Have you ever seen how the most popular candies in the United States are made? These products are assembled in ways you didn't even know were possible, and they have found the perfect way to make their candies. Today, we're showing you how Skittles, Sour Punch, and Starburst candies are made. Skittles rush through enormous rotating coating pans as a fine mist of fruit-flavored sugar syrup lands on thousands of tumbling candy centers, adding another paper-thin layer before warm air dries the surface again only moments later. The drums never stop turning. Every rotation exposes a different side of every candy, and every spray cycle builds the shell just a little thicker. What looks like a finished candy is actually changing constantly, because dozens upon dozens of nearly invisible layers still have to be added before the shell reaches its final crunch. Those colorful shells begin with something that looks nothing like a Skittle. Inside large stainless steel cooking kettles, granulated sugar, glucose syrup, and carefully measured water are combined under continuous agitation. Steam jackets surrounding the kettles raise the temperature gradually, while powerful mixers keep the syrup moving to prevent localized overheating. As moisture evaporates, the syrup becomes thicker and more concentrated. Its texture changes from a freely flowing liquid into a dense, glossy candy mass capable of holding its shape after cooling. Sensors continuously monitor temperature, concentration, and viscosity because every adjustment affects how the candy will behave later during forming. Once the cooking stage reaches the required concentration, carefully measured ingredients that influence texture and flavor are introduced through automated dosing systems. Organic acids, stabilizing ingredients, and other functional components disperse evenly throughout the circulating syrup, while computerized controls maintain constant mixing speed. The liquid still appears smooth and uniform, but internally it has reached the exact composition needed to become the chewy center hidden inside every Skittle. The hot candy mass leaves the cooking kettles through insulated pipelines and travels toward cooling equipment designed to lower its temperature without allowing it to harden completely. As the material moves across cooled stainless steel surfaces, it becomes firm enough to handle yet remains flexible enough to pass through forming equipment. The once flowing syrup now behaves more like a soft, dense dough, preparing it for one of the fastest stages in the factory. Extrusion equipment pushes the candy mass through specially designed dies that produce continuous ropes of identical diameter. Conveyor belts pull these ropes forward at carefully synchronized speeds so they remain perfectly uniform from beginning to end. Laser measuring systems constantly monitor thickness, while automatic controls make tiny adjustments to maintain consistency. Every future Skittle depends on these ropes remaining nearly identical because even slight differences would become much more noticeable after coating. The candy ropes soon reach rotary cutting equipment, where rapidly moving blades divide them into thousands of small pieces every minute. Freshly cut pieces tumble onto moving conveyors, but they still have flat ends and irregular edges from the cutting process. They resemble tiny cylinders rather than the familiar rounded candies found inside a package. Their biggest transformation is about to begin. The cut centers enter rotating polishing drums where constant movement slowly rounds every edge. As the pieces roll against one another, friction gradually softens the sharper corners while preserving the dense interior. This shaping process takes time because the goal is smooth consistency rather than aggressive reshaping. Drum speed, product load, and residence time remain carefully controlled, so every center develops a similar rounded profile before continuing. By the time the candies leave this stage, they have become noticeably smoother, though they still lack both their colorful shell and glossy finish. Before coating begins, the centers enter a conditioning area where temperature and humidity remain tightly controlled. During this stage, moisture redistributes evenly throughout every piece, while the exterior firms enough to withstand repeated coating cycles. Although very little appears to happen from the outside, this quiet preparation determines how successfully the later sugar layers will attach. A center that remains too soft could deform inside the coating pans, while one that becomes excessively dry would not accept new layers evenly. Now the process returns to the rotating coating drums, where the transformation becomes almost hypnotic. Thousands of conditioned centers tumble continuously while precision spray nozzles apply an extremely thin coating of concentrated sugar syrup. Immediately afterward, streams of warm conditioned air flow through the rotating drum, removing moisture from the fresh coating before another application begins. The cycle repeats again and again. Spray, tumble, dry, rotate. Each pass adds only a microscopic layer, yet the shell gradually grows stronger and thicker with every revolution. The remarkable part is how slowly the shell develops. Instead of pouring on one heavy coating, the factory builds the candy almost atom by atom compared with its final size. Every completed layer becomes the foundation for the next. Automated systems constantly monitor humidity, syrup flow, drum rotation speed, and air temperature because every variable influences surface smoothness. If drying happens too slowly, neighboring candies begin sticking together. If it happens too quickly, later coatings fail to bond perfectly. Maintaining that balance allows thousands of candies to grow simultaneously while remaining almost identical. Clear sugar layers continue accumulating until the shell reaches much of its intended thickness. At this point, another dramatic change begins. Separate stainless steel blending vessels have been preparing colored coating syrups throughout the earlier stages. Food colors disperse evenly into fresh sugar syrup before passing through filtration systems that remove even the smallest particles capable of affecting surface quality. Individual tanks prepare the vibrant red, orange, yellow, green, and purple solutions independently so each production line can receive exactly the required color. The candies return to rotating pans, but this time the sprayed syrup carries color as well as sugar. Each application deepens the appearance only slightly. One layer is barely noticeable, yet dozens of repeated applications gradually produce the brilliant shades associated with Skittles. The constant tumbling motion ensures every surface receives equal exposure while preventing flat spots or uneven buildup. Looking inside the drum, the candies seem to move randomly, but every rotation contributes to remarkably uniform coverage. Color alone is not enough. Another set of syrup systems now begins introducing concentrated fruit flavors. Depending on the production schedule, different coating lines prepare flavor blends corresponding to the candy colors. These flavor systems combine with fresh coating syrup before entering the spray nozzles. Every microscopic layer now contributes sweetness, aroma, and fruit character while continuing to strengthen the shell. Layer after layer builds the familiar balance between the chewy center and crisp exterior. Once the shell reaches its programmed thickness, the candies move into finishing drums where polishing begins. Small amounts of edible glazing ingredients are applied while the drums continue rotating. These coatings spread into an extremely thin protective film that increases shine while reducing surface friction between individual candies. As the polishing continues, the matte appearance gradually transforms into the glossy finish recognized immediately inside every bag of Skittles. Bright lighting above the conveyors reveals thousands of colorful candies reflecting light as they move toward the next stage. The candies now enter a controlled conditioning area for a second time. Although the shell appears complete, tiny amounts of remaining moisture continue redistributing throughout the coating. Temperature and humidity remain carefully regulated while the shell hardens fully. This final conditioning stage helps create the crisp bite that gives way to the softer, chewy center beneath. Rushing this step would leave the shell weaker and more vulnerable during packaging. Now every candy travels individually across high-speed inspection conveyors. Vibrating feeders separate the product into single layers before optical cameras examine each piece. Advanced vision systems evaluate color consistency, size, shape, surface quality, and coating completeness at extraordinary speed. Air jets positioned along the conveyor remove any candy showing visible defects, incomplete coating, or irregular dimensions. Only properly finished candies continue forward. Sour Punch candy ropes surge out of a long cooling tunnel in continuous colorful ribbons, still soft enough to bend, but already carrying the ridged shape that makes them instantly recognizable. Conveyor belts pull the endless strands forward with perfect synchronization, while rotating guide rollers keep every ribbon straight. They already look close to finished, but the stage waiting just ahead will completely transform both their flavor and texture. Within moments, those glossy ropes will disappear beneath a sparkling layer of sour sugar. Yet even that dramatic coating is only possible because of a long chain of carefully controlled manufacturing steps that began much earlier with a steaming mixture of syrup, sugar, and starch. The journey starts inside massive stainless steel mixing tanks where granulated sugar, corn syrup, and purified water are brought together under constant agitation. Large steam jackets wrapped around the vessels steadily raise the temperature, while heavy-duty agitators keep the mixture circulating without interruption. As the sugar dissolves completely, the once cloudy blend becomes a perfectly smooth syrup. Water gradually evaporates throughout the cooking process, increasing the concentration until the liquid grows thick and glossy. Temperature probes, flow meters, and computerized control systems monitor every stage continuously because the exact cooking profile determines how flexible the finished candy will remain after cooling. While the syrup continues concentrating, modified starches enter through automated dosing systems. Unlike the starches used for baked products, these carefully selected ingredients create the elastic, chewy structure that defines Sour Punch candy. Powerful mixers immediately disperse the starch throughout the hot syrup, preventing lumps while allowing every particle to hydrate evenly. The mixture becomes noticeably more resistant to movement as its internal structure develops. What started as a free-flowing liquid now behaves like a dense confectionery base capable of stretching without breaking. That unique texture is essential because the candy will soon be pulled, extruded, coated, and packaged without losing its distinctive chew. Acid systems are prepared separately before joining the cooked candy base. Carefully measured food acids dissolve completely inside smaller blending tanks, where their concentration can be controlled with exceptional precision. These solutions enter the main batch gradually while mixers continue circulating the candy mass. Rather than creating the intense sour finish found on the outside of the candy, these ingredients establish the balanced tartness hidden within the chewy center itself. Every addition is monitored closely because acidity influences both flavor and the way the candy behaves during processing. Next comes the stage that gives every Sour Punch variety its individual personality. Large blending vessels containing concentrated flavor systems feed directly into the candy mass through precision metering pumps. Depending on the production run, strawberry, blue raspberry, green apple, grape, watermelon, or tropical fruit formulations enter in carefully programmed quantities. Liquid colors are introduced through separate dosing equipment at nearly the same time, spreading rapidly through the warm mixture until every portion develops a completely uniform appearance. By the time blending finishes, the once clear confectionery base has become a brilliantly colored mass, carrying the exact flavor profile intended for that production line. The warm candy leaves the cooking vessels through insulated transfer pipes and enters vacuum processing equipment designed to remove tiny amounts of remaining moisture. Inside these chambers, pressure drops dramatically, allowing controlled evaporation at relatively low temperatures. This step fine-tunes the candy's final consistency while eliminating trapped air bubbles that could weaken the finished ropes. Pumps continuously circulate the dense candy through the system before sending it directly toward forming equipment. The material now has exactly the balance of flexibility and strength needed for the next transformation. Without stopping, the candy enters powerful extrusion systems fitted with specially engineered dies. Enormous, screws push the warm confectionery mass forward under carefully controlled pressure until it emerges as continuous flat ribbons. These dies do much more than determine width. Their internal geometry creates the signature ridges running the full length of every Sour Punch straw or strip. As the candy exits, the ridges appear immediately, formed with remarkable precision despite the continuous movement of the soft material. Conveyor belts positioned directly beneath the extrusion heads pull the ribbons away at perfectly synchronized speeds, preventing distortion while maintaining identical dimensions across every strand. Freshly extruded candy remains warm and extremely pliable, making cooling the next critical stage. The endless ribbons travel through long cooling tunnels where carefully conditioned air flows across both surfaces. Cooling happens gradually rather than suddenly, allowing the candy structure to stabilize without becoming brittle. As heat leaves the confection, the surface firms enough to support later handling while the interior retains its characteristic chewiness. Sensors distributed throughout the tunnel constantly monitor air temperature and humidity, automatically adjusting conditions to maintain consistent results regardless of production speed. As the ribbons emerge from the cooling tunnel, automated measuring systems verify width, thickness, and ridge definition. High-speed cameras inspect every continuous strip, while laser sensors detect even the smallest dimensional variations. If adjustments become necessary, computerized controls immediately alter extrusion pressure or conveyor speed without interrupting production. This constant feedback allows thousands of meters of candy to be produced with remarkable consistency. Now the ribbons approach one of the most recognizable stages in the entire process. Large coating stations wait beneath continuously moving conveyors, while specialized dispensing equipment showers the candy with a sparkling mixture of granulated sugar and food acids. The ribbons pass through from above, while vibrating spreaders distribute the coating evenly across every ridge and groove. Unlike the internal tartness created earlier, this outer coating delivers the sharp, immediate sour sensation that defines Sour Punch. Every crystal must adhere securely without forming thick clumps or leaving bare areas, making the balance between surface moisture and coating flow especially important. The freshly coated ribbons continue across gentle vibration conveyors that shake away excess sugar while leaving a uniform layer behind. The recovered coating falls into collection systems where it is filtered before returning to the application equipment. This constant circulation keeps... Have you ever seen how the most popular candies in the United States are made? These products are assembled in ways you didn't even know were possible, and they have found the perfect way to make their candies. Today, we're showing you how Skittles, Sour Punch, and Starburst candies are made. Skittles rush through enormous rotating coating pans as a fine mist of fruit-flavored sugar syrup lands on thousands of tumbling candy centers, adding another paper-thin layer before warm air dries the surface again only moments later. The drums never stop turning. Every rotation exposes a different side of every candy, and every spray cycle builds the shell just a little thicker. What looks like a finished candy is actually changing constantly, because dozens upon dozens of nearly invisible layers still have to be added before the shell reaches its final crunch. Those colorful shells begin with something that looks nothing like a Skittle. Inside large stainless steel cooking kettles, granulated sugar, glucose syrup, and carefully measured water are combined under continuous agitation. Steam jackets surrounding the kettles raise the temperature gradually, while powerful mixers keep the syrup moving to prevent localized overheating. As moisture evaporates, the syrup becomes thicker and more concentrated. Its texture changes from a freely flowing liquid into a dense, glossy candy mass capable of holding its shape after cooling. Sensors continuously monitor temperature, concentration, and viscosity because every adjustment affects how the candy will behave later during forming. Once the cooking stage reaches the required concentration, carefully measured ingredients that influence texture and flavor are introduced through automated dosing systems. Organic acids, stabilizing ingredients, and other functional components disperse evenly throughout the circulating syrup, while computerized controls maintain constant mixing speed. The liquid still appears smooth and uniform, but internally it has reached the exact composition needed to become the chewy center hidden inside every Skittle. The hot candy mass leaves the cooking kettles through insulated pipelines and travels toward cooling equipment designed to lower its temperature without allowing it to harden completely. As the material moves across cooled stainless steel surfaces, it becomes firm enough to handle yet remains flexible enough to pass through forming equipment. The once flowing syrup now behaves more like a soft, dense dough, preparing it for one of the fastest stages in the factory. Extrusion equipment pushes the candy mass through specially designed dies that produce continuous ropes of identical diameter. Conveyor belts pull these ropes forward at carefully synchronized speeds so they remain perfectly uniform from beginning to end. Laser measuring systems constantly monitor thickness, while automatic controls make tiny adjustments to maintain consistency. Every future Skittle depends on these ropes remaining nearly identical because even slight differences would become much more noticeable after coating. The candy ropes soon reach rotary cutting equipment where rapidly moving blades divide them into thousands of small pieces every minute. Freshly cut pieces tumble onto moving conveyors, but they still have flat ends and irregular edges from the cutting process. They resemble tiny cylinders rather than the familiar rounded candies found inside a package. Their biggest transformation is about to begin. The cut centers enter rotating polishing drums where constant movement slowly rounds every edge. As the pieces roll against one another, friction gradually softens the sharper corners while preserving the dense interior. This shaping process takes time because the goal is smooth consistency rather than aggressive reshaping. Drum speed, product load, and residence time remain carefully controlled, so every center develops a similar rounded profile before continuing. By the time the candies leave this stage, they have become noticeably smoother, though they still lack both their colorful shell and glossy finish. Before coating begins, the centers enter a conditioning area where temperature and humidity remain tightly controlled. During this stage, moisture redistributes evenly throughout every piece, while the exterior firms enough to withstand repeated coating cycles. Although very little appears to happen from the outside, this quiet preparation determines how successfully the later sugar layers will attach. A center that remains too soft could deform inside the coating pans, while one that becomes excessively dry would not accept new layers evenly. Now the process returns to the rotating coating drums, where the transformation becomes almost hypnotic. Thousands of conditioned centers tumble continuously while precision spray nozzles apply an extremely thin coating of concentrated sugar syrup. Immediately afterward, streams of warm conditioned air flow through the rotating drum, removing moisture from the fresh coating before another application begins. The cycle repeats again and again. Spray, tumble, dry, rotate. Each pass adds only a microscopic layer, yet the shell gradually grows stronger and thicker with every revolution. The remarkable part is how slowly the shell develops. Instead of pouring on one heavy coating, the factory builds the candy almost atom by atom compared with its final size. Every completed layer becomes the foundation for the next. Automated systems constantly monitor humidity, syrup flow, drum rotation speed, and air temperature because every variable influences surface smoothness. If drying happens too slowly, neighboring candies begin sticking together. If it happens too quickly, later coatings fail to bond perfectly. Maintaining that balance allows thousands of candies to grow simultaneously while remaining almost identical. Clear sugar layers continue accumulating until the shell reaches much of its intended thickness. At this point, another dramatic change begins. Separate stainless steel blending vessels have been preparing colored coating syrups throughout the earlier stages. Food colors disperse evenly into fresh sugar syrup before passing through filtration systems that remove even the smallest particles capable of affecting surface quality. Individual tanks prepare the vibrant red, orange, yellow, green, and purple solutions independently so each production line can receive exactly the required color. The candies return to rotating pans, but this time the sprayed syrup carries color as well as sugar. Each application deepens the appearance only slightly. One layer is barely noticeable, yet dozens of repeated applications gradually produce the brilliant shades associated with Skittles. The constant tumbling motion ensures every surface receives equal exposure while preventing flat spots or uneven buildup. Looking inside the drum, the candies seem to move randomly, but every rotation contributes to remarkably uniform coverage. Color alone is not enough. Another set of syrup systems now begins introducing concentrated fruit flavors. Depending on the production schedule, different coating lines prepare flavor blends corresponding to the candy colors. These flavor systems combine with fresh coating syrup before entering the spray nozzles. Every microscopic layer now contributes sweetness, aroma, and fruit character while continuing to strengthen the shell. Layer after layer builds the familiar balance between the chewy center and crisp exterior. Once the shell reaches its programmed thickness, the candies move into finishing drums where polishing begins. Small amounts of edible glazing ingredients are applied while the drums continue rotating. These coatings spread into an extremely thin protective film that increases shine while reducing surface friction between individual candies. As the polishing continues, the matte appearance gradually transforms into the glossy finish recognized immediately inside every bag of Skittles. Bright lighting above the conveyors reveals thousands of colorful candies reflecting light as they move toward the next stage. The candies now enter a controlled conditioning area for a second time. Although the shell appears complete, tiny amounts of remaining moisture continue redistributing throughout the coating. Temperature and humidity remain carefully regulated while the shell hardens fully. This final conditioning stage helps create the crisp bite that gives way to the softer, chewy center beneath. Rushing this step would leave the shell weaker and more vulnerable during packaging. Now every candy travels individually across high-speed inspection conveyors. Vibrating feeders separate the product into single layers before optical cameras examine each piece. Advanced vision systems evaluate color consistency, size, shape, surface quality, and coating completeness at extraordinary speed. Air jets positioned along the conveyor remove any candy showing visible defects, incomplete coating, or irregular dimensions. Only properly finished candies continue forward. Sour Punch candy ropes surge out of a long cooling tunnel in continuous colorful ribbons, still soft enough to bend, but already carrying the ridged shape that makes them instantly recognizable. Conveyor belts pull the endless strands forward with perfect synchronization, while rotating guide rollers keep every ribbon straight. They already look close to finished, but the stage waiting just ahead will completely transform both their flavor and texture. Within moments, those glossy ropes will disappear beneath a sparkling layer of sour sugar. Yet even that dramatic coating is only possible because of a long chain of carefully controlled manufacturing steps that began much earlier with a steaming mixture of syrup, sugar, and starch. The journey starts inside massive stainless steel mixing tanks where granulated sugar, corn syrup, and purified water are brought together under constant agitation. Large steam jackets wrapped around the vessels steadily raise the temperature, while heavy-duty agitators keep the mixture circulating without interruption. As the sugar dissolves completely, the once cloudy blend becomes a perfectly smooth syrup. Water gradually evaporates throughout the cooking process, increasing the concentration until the liquid grows thick and glossy. Temperature probes, flow meters, and computerized control systems monitor every stage continuously because the exact cooking profile determines how flexible the finished candy will remain after cooling. While the syrup continues concentrating, modified starches enter through automated dosing systems. Unlike the starches used for baked products, these carefully selected ingredients create the elastic, chewy structure that defines sour punch candy. Powerful mixers immediately disperse the starch throughout the hot syrup, preventing lumps while allowing every particle to hydrate evenly. The mixture becomes noticeably more resistant to movement as its internal structure develops. What started as a free-flowing liquid now behaves like a dense confectionery base capable of stretching without breaking. That unique texture is essential because the candy will soon be pulled, extruded, coated, and packaged without losing its distinctive chew. Acid systems are prepared separately before joining the cooked candy base. Carefully measured food acids dissolve completely inside smaller blending tanks where their concentration can be controlled with exceptional precision. These solutions enter the main batch gradually while mixers continue circulating the candy mass. Rather than creating the intense sour finish found on the outside of the candy, these ingredients establish the balanced tartness hidden within the chewy center itself. Every addition is monitored closely because acidity influences both flavor and the way the candy behaves during processing. Next comes the stage that gives every sour punch variety its individual personality. Large blending vessels containing concentrated flavor systems feed directly into the candy mass through precision metering pumps. Depending on the production run, strawberry, blue raspberry, green apple, grape, watermelon, or tropical fruit formulations enter in carefully programmed quantities. Liquid colors are introduced through separate dosing equipment at nearly the same time, spreading rapidly through the warm mixture until every portion develops a completely uniform appearance. By the time blending finishes, the once clear confectionery base has become a brilliantly colored mass, carrying the exact flavor profile intended for that production line. The warm candy leaves the cooking vessels through insulated transfer pipes and enters vacuum processing equipment designed to remove tiny amounts of remaining moisture. Inside these chambers, pressure drops dramatically, allowing controlled evaporation at relatively low temperatures. This step fine-tunes the candy's final consistency while eliminating trapped air bubbles that could weaken the finished ropes. Pumps continuously circulate the dense candy through the system before sending it directly toward forming equipment. The material now has exactly the balance of flexibility and strength needed for the next transformation. Without stopping, the candy enters powerful extrusion systems fitted with specially engineered dies. Lay's crisps leave the fryer as thin golden slices, still shimmering with hot oil before seasoning turns them into finished chips. The slices ride up an inclined conveyor with open gaps beneath them. Oil drains away as the chips move forward. They are fragile at this point. Their surfaces are crisp, blistered, and lightly curled from the sudden loss of moisture inside the fryer. Air moves across the belt to cool them just enough for seasoning to cling correctly. The fryer is the center of the transformation. Raw potato slices enter pale, wet, and flexible. A few seconds later, they are crisp, rigid, and golden. Hot oil surrounds each slice. Water inside the potato flashes into steam and escapes as bubbling. The slice becomes thinner as moisture leaves. Starch gelatinizes first then dries into a brittle structure. Oil temperature is controlled across the fryer. If the oil is too cool, the slices absorb too much oil and turn heavy. If it is too hot, the outside darkens before the center dries. The conveyor speed controls how long each slice remains in the oil. The result must be a crisp chip with a light golden color and clean break. Loose fragments and small potato solids fall away during frying. A filtration system continuously removes these particles from the oil. This prevents dark specks from burning and sticking to later chips. Fresh oil is added in controlled amounts to maintain the frying system. Before the fryer, the potatoes are sliced with high-speed cutting heads. Whole peeled potatoes enter a rotating slicer. Sharp blades shave them into very thin sheets. The slice thickness is tightly controlled because even a small change affects texture, cook time, color, and crunch. The cutting action is fast and clean. Each potato spins or passes against the blades, producing a stream of round or oval slices. The slices fall into a water flume immediately after cutting. Water separates them from each other and carries away free starch from the cut surfaces. Surface starch must be reduced before frying. Too much starch can make slices stick together or darken unevenly. The slices pass through washers where moving water lifts starch from the surface. The water becomes cloudy as starch leaves the potato. After washing, the slices move through dewatering equipment. Shaker conveyors and air knives remove surface water. If wet slices enter the fryer, oil turbulence increases and frying becomes less controlled. The slice must still be raw and moist inside, but the outside cannot carry excess water. The potatoes reach the slicer after a long preparation route. Whole potatoes arrive at the factory in bulk. They are unloaded into receiving hoppers and carried by conveyors toward cleaning equipment. Dirt, stones, vines, and field debris must be removed before the potatoes reach the process line. A dry separation stage removes loose soil and heavy objects. Rollers, screens, and conveyors shake the potatoes while smaller debris falls away. Stones can be separated by density systems because they behave differently from potatoes in water or mechanical sorting. The potatoes then enter washing drums. Water sprays across them while rotating drums tumble the load. The skins rub against each other and against the drum surface. Soil loosens and drains away with the wash water. The potatoes leave cleaner, smoother, and ready for inspection. Sizing equipment separates potatoes by diameter. Very small potatoes do not slice into the right chip size. Oversized potatoes may be diverted or trimmed. Uniform sizing helps the slicer produce consistent chips and helps the fryer cook them evenly. Some potatoes move through peeling equipment. Steam peeling uses high-pressure steam to loosen the skins quickly. When pressure drops, the skin separates from the flesh. Brushes or rollers remove the loosened skin. Other lines use abrasive peeling, where rough surfaces rub the skin away. After peeling, the potatoes pass through inspection and trimming systems. Optical sorters examine the surface for dark spots, green areas, bruises, or defects. Jets of air or mechanical diverters remove potatoes that do not meet the program limits. The accepted potatoes continue towards slicing. Potato variety and solids level matter for crisp production. A good chip potato has enough dry matter to fry into a crisp slice without becoming leathery. Potatoes with too much sugar can brown too quickly. Potatoes with too much water require longer frying and may produce weak texture. Once the raw slices are washed, dewatered, and fried, they enter the seasoning system. The chips leave the fryer and pass through a cooling zone before entering a rotating seasoning drum. The drum is tilted slightly and turns continuously. Chips enter at one end and tumble gently toward the other. The rotation exposes different surfaces without crushing the chips. Seasoning is applied as a fine powder through controlled feeders. For classic salted Lay's, salt. Crystals are metered onto the chips while they are still warm and lightly oily. The oil film helps the salt stick. For flavored varieties, powders contain salt, spices, dairy powders, onion, garlic, cheese flavors, barbecue seasoning, sour cream flavor, vinegar components, or other dry ingredients. The seasoning feeder must deliver a steady flow. If too much powder drops at once, some chips become overloaded while others remain plain. If too little is applied, the flavor becomes weak. The drum angle, rotation speed, chip flow rate, and powder rate work together. Inside the drum, chips slide, lift, fall, and rotate. The seasoning dust spreads across curves, blisters, and edges. The sound changes from the sharp crackle of dry chips to a softer rattling as powder coats the surfaces. The chips exit evenly seasoned and ready for inspection. Broken chips and tiny fragments are separated before packaging. Vibrating conveyors can remove fines through small openings. Optical systems inspect color and detect dark chips or burnt pieces. Metal detectors scan the product stream. Defective material is diverted automatically. The accepted chips move to weighing. Because chips are light and irregular, they cannot be filled by simple volume. A multi-head weigher is used. Chips feed into multiple small weighing buckets positioned around the machine. Each bucket holds a small portion. The control system calculates which combination of buckets adds up to the target bag weight. Those buckets open together, dropping the exact portion into a funnel. The chips fall quickly, but must not be crushed. Smooth surfaces and controlled drop heights protect the fragile pieces. Packaging film unwinds below the weighing system. The film is printed on the outside and has barrier layers that help protect crispness. It moves over a forming collar, which shapes it into a vertical tube. The edges of the film meet at the back. A vertical sealing jaw closes the back seam. The bottom seal is made first by horizontal jaws. Then the weighed chips drop into the open tube. The jaws close again above the product, sealing the top of one bag and the bottom of the next. Before final sealing, nitrogen gas may flush the package. The gas reduces oxygen and creates a cushion inside the bag. The pillow shape protects chips from crushing and helps preserve crisp texture. The bag is not filled tightly with chips. It contains product and protective headspace. The horizontal jaws cut between seals, releasing one finished bag. The next bag is already forming above it. This process repeats rapidly, turning a continuous roll of film and timed chip portions into sealed Lay's bags. A naked Snickers center enters the enrober with its layers exposed. The bottom layer is pale nougat. The top layer is caramel packed with roasted peanuts. The sides show the cut structure clearly, with soft nougat below and darker caramel above. It already has the shape of a bar, but it is not finished until chocolate surrounds every exposed surface. The center rides on a wire mesh belt. Ahead of it, tempered milk chocolate circulates through a coating system. A pump lifts the chocolate into an overhead trough. From there, it falls as a smooth curtain across the full width of the conveyor. The center passes through the curtain. Chocolate flows over the peanut caramel top first, then down the sides and across the cut ends. At the same time, a lower coating stream covers the underside through the open mesh belt. The bar becomes enclosed from all directions. Excess chocolate drains away through the belt and returns to the reservoir. Air blowers remove extra coating from the top and edges. The airflow smooths the surface and controls shell thickness. Too much chocolate would bury the shape. Too little would expose peanuts, nougat, or caramel. A short vibrating section helps the chocolate settle. Tiny air bubbles rise from the coating. The liquid shell rounds the corners and fills small uneven spaces around peanuts near the surface. The bar now looks finished, but the chocolate is still soft. Before this enrobing stage, the center is built as a wide layered slab. The nougat layer begins with a cooked sugar syrup. Sugar, glucose syrup, and water are measured into a cooker. Heat drives off moisture, making the syrup thicker and more concentrated. The syrup must reach the correct solids level because it controls the chew and stability of the nougat. In a separate mixer, an aerating base is prepared. A whipping ingredient is hydrated and beaten until it can hold fine air bubbles. The hot syrup streams into this foam while the mixer turns. The foam becomes stronger and heavier as the syrup blends through it. The mixture changes from light foam into dense confectionery nougat. It traps many small air cells, giving the layer a softer bite than caramel. Milk ingredients, fat, peanut flavor components, and other formula additions are folded in. The mixer works the mass until it becomes uniform. The nougat must be soft enough to bite through, but strong enough to support caramel and peanuts. If it is too weak, the bar compresses during cutting. If it is too dense, the center loses its light chew. The finished nougat leaves the mixer as a warm, elastic mass. It is deposited onto a forming belt. Rollers spread it into a continuous sheet. Side guides control width, and calibrated rollers set thickness. The surface becomes flat enough to receive the next layer. The nougat sheet enters a cooling section. Cool air firms its surface while the inside remains chewy. This prevents the caramel layer from sinking too deeply into it. The caramel layer is produced separately. Sugar, glucose syrup, milk ingredients, fat, and water enter heated kettles or continuous cookers. The mixture starts pale and fluid. As water evaporates, the liquid thickens, darkens, and becomes glossy. Agitators keep the mass moving so it cooks evenly. The caramel must have a stretchable texture. It needs to hold peanuts in place, but it also needs to pull, rather than snap when bitten. Cooking temperature, moisture level, and cooling temperature all control this behavior. Roasted peanuts are prepared on their own line before they reach the caramel. The peanuts pass through cleaning and sizing equipment. Screens remove small fragments and oversized pieces. Airflow pulls away skins and loose material. The accepted peanuts move into a roaster. Inside the roaster, hot air moves through the peanut bed. Moisture leaves the nuts. The texture becomes crisp. The peanuts develop the firmness needed to survive mixing and cutting without turning into powder. The roasted peanuts leave the heat and enter cooling. Air draws away heat quickly, stopping further roasting. After cooling, they pass through another screening stage. Broken pieces, skins, and undersized fragments are separated from the mainstream. The caramel and peanuts meet shortly before layering. Warm caramel flows through a mixing section, while peanuts are metered in at a controlled rate. The nuts become coated by caramel and spread throughout the mass. The mixture becomes thick, heavy, and textured. This peanut caramel mass is deposited across the cooled nougat sheet. A wide slot nozzle or depositor lays it down as a continuous band. Leveling equipment spreads it evenly from side to side. The peanuts must be distributed consistently so every cut bar contains the same type of layer. The two-layer slab now moves through a setting tunnel. Cool air firms the caramel enough for cutting. The slab remains flexible, but it can hold its shape under knives. The nougat, caramel, and peanuts bond into one continuous sheet. The slab reaches the slitting station. Long circular knives cut it lengthwise into narrow ropes. Each rope shows the same cross-section. The knives must pass through peanuts cleanly without dragging caramel down the sides. The ropes move apart slightly. A crosscutter then divides them into individual bar lengths. The blade moves in rhythm with the conveyor. Each cut produces a center with squared ends and exposed layers. The centers may pass through a conditioning zone before chocolate coating. Their surface temperature must match the enrobing conditions. Warm centers can make chocolate slide. Cold centers can make chocolate set before it spreads. The chocolate used for coating is prepared in another system. Cocoa ingredients, sugar, milk powder, cocoa butter, and fats are mixed into a thick chocolate mass. The mixture passes through refining rollers that reduce particle size. This creates a smooth texture instead of a gritty one. The refined chocolate moves into conching equipment. Heavy arms work the mass under controlled heat. Fat spreads around the dry particles. The chocolate becomes smoother and more fluid. Before the chocolate reaches the enrober, it is tempered. It is cooled and gently warmed through a specific temperature sequence. This creates stable cocoa butter crystals. Tempered chocolate sets into a firm shell with a smooth surface after cooling. The conditioned Snickers centers then enter the enrober, where the chocolate curtain covers them completely. After the blowers and vibration section, the coated bars move into the cooling tunnel. Chilled air flows around the bars from above and below. The chocolate begins to crystallize. The surface changes from liquid shine to a firm shell. The soft nougat and caramel remain inside, protected by the coating. Cooling is controlled carefully. If it is too fast, the shell can crack or look dull. If it is too slow, the bars smear on belts and guides. The tunnel balances belt speed, temperature, and airflow until the coating is stable. At the exit, the bars pass through inspection. Cameras check coating coverage, broken corners, exposed caramel, exposed nougat, surface marks, incorrect length, and deformed shape. Metal detectors scan the product stream. Bars outside the programmed limits are rejected automatically. Accepted bars move toward wrapping. Timing belts space them evenly. Guide rails align each bar lengthwise so it enters the wrapper straight. Printed film unwinds from a roll. Tension rollers keep the film smooth. Registration sensors read printed marks and synchronize the wrapper graphics with each bar. The film folds around the bar through a forming box. A longitudinal seal closes along the underside or back. Heated sealing wheels press the film layers together while the bar continues moving. Cross-seal jaws close the front and back ends of each pack. They seal and cut at the same time, separating one wrapped Snickers from the continuous film tube. Wrapped bars pass through check weighers. A broken bar, missing bar, or incorrect product creates a weight outside the target range and is rejected. Vision systems inspect seal quality, wrapper alignment, code placement, and print registration. A coding unit applies production information to the wrapper or outer pack. The mark is small, sharp, and placed while the pack moves at full speed. Single bars may move directly to case packing. Multi-pack formats branch into another grouping stage. Several wrapped bars are gathered by belts and mechanical guides. The group enters a secondary film wrapper or paperboard carton. Poppy production begins with a sharp apple cider vinegar ingredient stream being measured into a much larger beverage base. The vinegar is not added loosely. It moves through a controlled dosing line with pumps measuring the amount before it enters the blending system. Because the flavor is strong and acidic, the dose must spread evenly through the full batch. The tank is already moving before the stream enters. Treated water is the main liquid. Incoming water passes through filtration to remove suspended particles. Carbon filtration reduces unwanted taste and odor. Final polishing stages create a clear, neutral base. This water is stored in sealed stainless steel tanks before blending. A measured quantity of treated water enters the main blend tank. The agitator starts turning below the surface. Its blades pull the water downward and push it outward along the tank wall. The movement creates a full tank circulation pattern, so later additions do not remain concentrated in one area. The apple cider vinegar stream enters beneath the surface. It folds into the moving water and quickly disperses. The acidity changes the base before sweetener or flavor is fully built. The liquid remains clear, but its sharp profile is now established. Sweetener is added next. Poppy-style drinks usually use a lighter sweetening system than a full sugar soda, so the sweetener amount is much smaller than in a traditional syrup room. The sweetener may enter as a liquid solution or as a prepared blend that dissolves quickly. The agitator continues moving. Sweetness spreads through the acidic water and softens the sharp edge of the vinegar. The base becomes balanced enough to carry fruit flavor, but it is still flat and uncarbonated. Prebiotic fiber ingredients are prepared carefully because they must dissolve cleanly and remain stable in the drink. A small preparation tank may receive treated water first. The fiber ingredient is added slowly while mixing prevents clumps. Once fully dispersed, this solution is pumped into the main blend. The fiber stream enters through a closed line. Flow meters confirm the addition. The main tank pulls the stream into circulation and spreads it through the beverage. The liquid must stay smooth, with no visible particles or thick sections. Acid balance is adjusted after the vinegar and fiber stream are in the tank. Fruit-flavored sparkling drinks need a controlled bright taste, not a harsh one. Additional acid or buffering ingredients can be metered in depending on the flavor. The tank mixes until the liquid reaches a uniform base condition. Flavor concentrate enters through another dosing line. Strawberry lemon, raspberry rose, orange, grape, cherry limeade, watermelon, or other varieties can be produced by changing the concentrate connected to the blending system. The concentrate is small in volume but strong in effect. The flavor stream hits the moving liquid and disappears. The tank turns the sharp, lightly sweetened base into a specific flavor profile. The mixture must be uniform before carbonation because once the drink is in pressurized piping, there is little opportunity for heavy correction. Color ingredients may be added depending on the variety. Some poppy drinks remain lightly tinted. Others take on a brighter fruit color. The color stream is metered in carefully. A very small amount changes the entire tank, so mixing continues until no streaks remain. The beverage base now contains treated water, vinegar, sweetener, fiber solution, acid balance, flavor, and color. It is still not finished. It must be clarified through filtration or strainers if the formula requires it, then chilled and carbonated. The liquid moves through a fine filtration stage. This step removes undissolved specks and protects later valves and filler nozzles. The drink must remain clean and smooth as it travels through high-speed equipment. The filtered base flows into a balance tank before final processing. Pumps pull from this tank and send the beverage toward cooling. Flow remains steady so the carbonation system receives an even supply. The drink enters a plate heat exchanger. It travels through narrow stainless steel passages. On the other side of the plates, a chilled medium removes heat. The beverage temperature drops quickly while the liquid remains sealed inside the system. Cold liquid absorbs carbon dioxide more efficiently than warm liquid. Cooling also reduces foam when the beverage enters cans. This is important because poppy is packaged as a sparkling drink, and uncontrolled foam would interfere with accurate fills. The chilled beverage may pass through a deaerator. Reduced pressure pulls dissolved air out of the liquid. Tiny bubbles rise and separate from the stream. Removing excess air helps the carbon dioxide dissolve more cleanly and keeps the drink's carbonation consistent. Carbon dioxide enters through regulated gas lines. Pressure control equipment stabilizes the gas before it reaches the carbonator. Inside the carbonator, chilled poppy meets carbon dioxide under pressure. The gas dissolves into the drink and creates the sparkling texture. From this point onward, the beverage stays inside pressurized stainless steel piping. The system keeps carbon dioxide dissolved until the can is sealed. The finished drink travels directly toward the filler. Empty aluminum cans move on a separate line. They arrive already formed, decorated, and open at the top. The cans are thin and lightweight, but they are designed to hold internal pressure once sealed. Guide rails organize the cans into single file movement. The cans enter an air rinser. Curved tracks turn each can upside down. Filtered air blasts the inside, removing loose particles. The cans rotate upright again and continue toward filling. The rotary filler receives the cans through a star wheel. The star wheel spaces every can beneath a filling valve. Above the valves, the filler bowl holds chilled, carbonated poppy under controlled pressure. Each can reaches its valve. Pressure and flow are controlled so the drink enters smoothly. The valve opens and the sparkling liquid flows into the can. Foam is held low by the cold temperature and the controlled filling environment. The fill level rises quickly. When the target volume is reached, the valve closes. A small headspace remains at the top. This space allows the lid to be applied and the sealed can to hold carbonation properly. The filled can moves immediately to lid placement. Aluminum lids are fed from stacked magazines. A lid separator releases one lid at a time and places it over the open can. The can enters the seamer. The can body and lid rotate together. The first seaming roll curls the lid edge around the can flange. The second roll compresses the folded metal into a tight double seam. The seal is mechanical, created by folded aluminum rather than glue. The sealed can exits with the sparkling drink trapped inside. Inspection begins immediately. Fill level sensors check the amount of liquid. Cameras examine lid placement, printed surface condition, dents, and overall can shape. Seam inspection checks the closure profile. A defective can is rejected by an air jet or mechanical pusher. Accepted cans continue in a steady stream toward coating. An inkjet printer marks production information on the can base or another assigned location. The code is applied while the can moves at full speed. A vision system can verify that the code is present and readable. Hershey's chocolate production begins when a thick brown chocolate mass is squeezed between refining rollers until its coarse texture becomes smooth enough for a finished bar. The mixture entering the refiner is not ready to mold. It contains cocoa ingredients, sugar, milk components, cocoa butter, and other fats blended into a heavy paste. The particles are still too large. If the bar were made at this stage, the texture would feel gritty instead of smooth. The refiner uses closely spaced rollers to reduce the particle size. The chocolate paste is pulled through narrow gaps under pressure. Each pass breaks down sugar crystals, cocoa particles, and milk solids into a finer structure. The paste becomes thinner in texture, more uniform, and better suited for the next stage. Before the chocolate reaches this point, the cocoa stream begins with roasted cocoa beans. The beans are cleaned, sorted, and roasted to develop flavor and loosen the outer shells. After roasting, the beans pass through cracking equipment. The brittle shells break away from the inner cocoa nibs. Winnowing equipment separates the lighter shells from the heavier nibs using airflow and screening. The nibs continue into grinding. As they are crushed, cocoa butter inside the nibs melts from the heat of friction, turning the dry pieces into a flowing cocoa liquor. This dark liquid becomes one of the main foundations of the chocolate. Milk chocolate production also needs milk ingredients. Milk powder or other prepared milk components are measured into the mixing system. Sugar is dosed separately. Cocoa butter or additional fat is added to control flow and texture. The ingredients come together in mixers that fold the dry and liquid phases into a uniform paste. This paste is the material that enters the refining rollers. Once refined, it moves into conching equipment. Conching is a long mechanical working stage. Heavy arms, rollers, or blades push and fold the chocolate continuously under controlled temperature. Inside the conche, the chocolate becomes smoother and more fluid. Fat spreads around the tiny dry particles. The mass loses rough edges in texture and develops the flow needed for molding. The movement is slow, heavy, and constant, like thick liquid being polished from inside. The chocolate's viscosity is adjusted during this stage. It cannot be too thick, or it will not flow cleanly into molds. It cannot be too thin, or it will not hold the correct bar structure. The conche brings the chocolate toward the exact behavior needed for high-speed depositing. After conching, the chocolate passes through storage tanks. These tanks keep it warm and moving. Slow agitators prevent settling and maintain even temperature. From here, the chocolate is pumped toward tempering. Tempering is the stage that prepares the chocolate to set correctly. The warm chocolate is cooled, then gently reheated through a controlled temperature curve. This creates stable cocoa butter crystals inside the liquid chocolate. Without proper tempering, the finished bar could become soft, dull, streaked, or weak. Properly tempered chocolate sets with a firm structure, smooth surface, and clean break. The liquid remains pumpable, but its internal crystal structure is ready for molding. The tempered chocolate flows into the molding line. Rows of empty bar molds move beneath depositor nozzles. The molds are usually made from rigid plastic or metal and contain the exact shape of the finished Hershey's bar, including its rectangular outline and raised segmented pattern. The depositor releases a measured amount of chocolate into each mold cavity. The chocolate spreads across the base and into the corners. It fills the raised letter and segment details from below, because the mold holds the bar pattern in reverse. The molds pass through a vibrating table immediately after filling. The vibration settles the chocolate and removes trapped air bubbles. Small bubbles rise to the surface and break. The chocolate levels out, filling every corner and detail of the mold. The filled molds now enter a cooling tunnel. Chilled air flows around them while the chocolate begins to crystallize. The surface touching the mold firms first. The center of the bar sets more slowly. The stable crystals created during tempering guide the full bar into a solid structure. Cooling must be carefully controlled. If it is too fast, the bar can contract unevenly or form surface defects. If it is too slow, the chocolate remains soft and cannot release from the mold cleanly. The tunnel balances air temperature, humidity, and travel time. As the bar cools, it contracts slightly. This small shrinkage helps it separate from the mold surface. When the mold reaches the demolding area, the chocolate is firm enough to release without bending. The molds invert or flex lightly. Mechanical taps or vibration help the bars drop onto a conveyor. Each bar lands with its molded face upward or is turned into the correct orientation for wrapping. The surface now shows the familiar segmented shape. The empty molds return to the filling station. They may pass through inspection or cleaning before receiving the next chocolate deposit. The molding loop continues continuously, with empty molds becoming filled molds, cooled molds, demolded molds, and empty molds again. The demolded bars move through inspection. Cameras check shape, surface marks, missing corners, air holes, dull patches, broken segments, and incorrect release. Bars outside the program limits are removed automatically. Metal detection scans the product stream before wrapping. Accepted bars continue toward the wrapping line. Timing belts space them evenly. Guide rails align each bar lengthwise. The wrapper must meet every bar at the same position, so spacing and orientation are tightly controlled. For a standard chocolate bar, printed wrapper film or foil-backed material unwinds from large rolls. Tension rollers keep the material smooth. Registration sensors read printed marks, so the wrapper design lines up correctly with the chocolate. The bar enters a flow wrapping system. The wrapper folds around it to form a tight package. A longitudinal seal closes along the back or underside. Heated sealing wheels press the material together while the bar continues forward. Cross-seal jaws close the two ends of the wrapper. They seal and cut the package from the continuous film. Each wrapped bar leaves as a separate unit with the chocolate protected inside. Some Hershey's bar formats use an inner wrap and an outer paper band. In that route, the chocolate first receives a protective foil or film layer. Then a printed paper wrapper folds around the outside. Folding plates, belts, and tucking fingers create crisp edges around the rectangular bar. Miniature bars follow the same basic idea on smaller equipment. Small molded pieces are aligned, wrapped in individual foil or film, sealed, coated, and sent toward bagging or carton packing. For bars containing inclusions, the chocolate process changes before molding. Almonds, crisped rice, cookie pieces, or other inclusions are prepared separately and fed into the tempered chocolate stream or deposited into the molds. The pieces must be dry and correctly sized so they do not clog nozzles or create weak spots. When inclusions are mixed into the chocolate, gentle agitation keeps them suspended. The depositor must deliver both chocolate and pieces evenly into every mold. The vibrating stage settles the mixture without allowing all inclusions to sink to one side. For filled or layered chocolate products, a shell molding process may be used. Chocolate is deposited into molds, then shaken or inverted to coat the cavity walls. After partial cooling, a filling is added, and more chocolate seals the base. The finished piece is cooled, demolded, inspected, and wrapped in a similar downstream sequence. For the classic solid bar, the process remains focused on molding a single continuous chocolate body. The segmented pattern helps the bar break into pieces later, but inside the factory, it also gives the product a precise shape that inspection systems can measure. Wrapped bars pass through check weighers. A missing bar, broken bar, or incorrect product weight causes rejection. Vision systems inspect wrapper position, seal quality, code presence, print alignment, and package damage. 7-Up production begins with a clear, lemon-lime base that must stay bright, transparent, and free of visible particles from the first mixing stage. Treated water enters the blending room through closed stainless steel pipework. Before it reaches the tank, the water has already passed through filtration stages that remove suspended particles. Carbon treatment removes unwanted taste and odor. Final polishing creates a consistent liquid base that will not interfere with the clean lemon-lime flavor. The treated water collects in a sealed storage tank. Sensors measure level, temperature, and flow. A pump sends a controlled volume into the main dissolving vessel. The tank interior is smooth and polished, so the liquid can circulate without dead spots. The agitator begins turning before sweetener is added. Its blades pull the water downward and drive it outward in a steady loop. This motion prepares the tank for sugar, liquid sweetener, or another specified sweetening system. Sweetener enters through a dosing line. If granulated sugar is used, the crystals fall into the moving water and dissolve as the liquid rotates. If liquid sweetener is used, it flows in as a dense stream and blends into the water more quickly. The tank keeps the liquid moving until the base is uniform. The sweetened liquid remains clear. It does not darken like cola syrup or become opaque like some fruit-flavored drinks. The mixture becomes slightly heavier and glossier, but it must keep a clean appearance. The sweet base passes through fine filtration. Small undissolved particles are removed before the beverage reaches flavoring and carbonation equipment. This protects the later valves and meters, but it also helps preserve the transparent look of the finished drink. A lemon-lime flavor concentrate is prepared in a separate dosing system. It is strong, aromatic, and added in a small amount compared with the full batch volume. Metering pumps push it through a narrow stainless steel line into the moving sweet base. The concentrate disappears into the tank without changing the liquid into a dark or cloudy drink. The agitator folds the flavor through the full volume. Because 7-Up is a clear soda, the flavor components must disperse evenly and remain stable without visible separation. Acid ingredients are introduced next. They create the sharp citrus structure that balances the sweetness. The acid stream is metered into the tank below the surface, where the moving liquid immediately pulls it through the base. The liquid is mixed until sweetness, acidity, and flavor strength are consistent. The tank does not rely only on time. Flow meters, temperature readings, and recipe controls keep the batch inside its target range. At this stage, the beverage base is strong and still. It has lemon-lime flavor, sweetness, and acidity, but it may not yet be at final drinking strength. If the process uses a concentrated syrup system, the base moves to a proportioner. The proportioner receives two streams. One stream carries the strong lemon-lime syrup. The second stream carries treated water from storage. Each stream passes through a flow meter before blending. The machine constantly compares the two flows. If the water stream rises, the syrup stream adjusts. If syrup pressure shifts, the water valve corrects. This keeps the final ratio stable across thousands of bottles or cans. Inside the blending chamber, the syrup thins instantly. The drink reaches finish strength while remaining clear and flat. It has no sparkle yet. It is still a non-carbonated lemon-lime beverage at this point. The flat 7-Up moves into cooling equipment. It passes through a plate heat exchanger. The beverage travels through narrow channels between stainless steel plates. A chilled medium moves on the opposite side of those plates and pulls heat away. The temperature drops quickly. Cooling is essential because cold liquid absorbs carbon dioxide more efficiently. It also fills more cleanly later, with less foam and less gas loss. The beverage may pass through a deaeration vessel. Reduced pressure draws dissolved air out of the liquid. Tiny bubbles rise from the stream and separate before the drink continues. Removing excess air gives carbon dioxide more room to dissolve and helps the finished soda behave consistently. Carbon dioxide enters through regulated gas lines. The gas passes through pressure control equipment before reaching the carbonator. Inside the carbonator, cold 7-Up meets carbon dioxide under pressure. The gas dissolves into the liquid, forming the sharp, sparkling bite. The drink is now finished and carbonated. From this point onward, it stays in closed pressurized pipes. The system keeps the gas inside the liquid until the container is sealed. While the beverage is being prepared, empty containers are moving through their own lines. For plastic bottles, the process begins with PET preforms. These are short, thick plastic tubes with finished neck threads. The neck is already complete. The body is still compact and must be expanded into the final bottle shape. The preforms enter a heating oven. Infrared lamps warm the plastic body as each preform rotates. Rotation prevents one side from heating faster than the other. The neck area stays cooler, so the threads and sealing surface keep their exact dimensions. A heated preform moves into a blow mold. The mold closes around it. A stretch rod drives downward through the softened plastic, pulling it lengthwise. Compressed air then expands the plastic outward against the chilled mold wall. The bottle forms instantly. The base, shoulders, grip panels, and label area appear as the plastic presses into the mold. The mold opens, and the empty bottle exits by its neck ring. The bottles move through air conveyors toward rinsing. Because the bottles are very light before filling, they are supported by the neck rather than pushed heavily along the base. Airflow moves them forward in a controlled stream. At the rinser, each bottle is gripped, inverted, and cleaned internally with filtered air or treated rinse water. The bottle drains, rotates upright, and moves toward the filler. Can lines prepare a different container? Aluminum cans arrive already shaped and printed with open tops. They pass through an air rinser, turn upside down, receive a blast of filtered air, and return upright before filling. Glass bottle lines begin with formed bottles. Cameras and light systems inspect the mouth, base, sidewall, and interior. Any bottle with a crack, chip, or visible defect leaves the line before filling. The carbonated 7-Up arrives at the filling machine through pressurized piping. The filler is a rotary carousel with many filling valves arranged around a central bowl. Containers enter through a star wheel that spaces them precisely. Each bottle or can aligns under a filling valve. Because the drink is carbonated, the filling system controls pressure before liquid enters. The container is sealed against the valve, and internal pressure is balanced with the filler environment. The valve opens. Clear sparkling 7. Up flows into the container. In a transparent bottle, the liquid rises almost invisibly, except for the fine bubbles forming along the wall. The fill level reaches the programmed height, and the valve closes. The filled container moves immediately to sealing. Plastic bottles travel under capping heads. Caps arrive from a sorter in the correct orientation. Each head places one cap on the threaded neck and tightens it to a set torque. The tamper band locks below the neck ring. Cans move into a seamer. A thin aluminum lid is placed over the filled can. The can and lid rotate together while seaming rolls fold the lid curl around the can flange. A second roll compresses the folded metal into a tight double seam. Glass bottles receive crown caps. The capper presses a metal crown onto the mouth and crimps its edge beneath the glass bead. The closure traps carbonation inside the bottle. Sealed containers pass through inspection. Fill level sensors check the amount of liquid. Cameras examine caps, crowns, can seams, bottle shape, and printed surfaces. Low fills, high fills, crooked caps, weak seams, and damaged containers are rejected automatically. Bottles move toward labeling after inspection. Since 7, up is clear, bottle and label alignment matter visually. The label must sit evenly around the container without covering the wrong panel or twisting across the body. For roll-fed labels, printed film unwinds from a reel. Registration sensors locate the print marks. A cutter separates each label. Adhesive attaches the leading edge to the bottle, and the bottle rotates as the film wraps around it. The trailing edge is sealed into place. Some formats use pressure-sensitive labels. These peel from a backing web and press onto the bottle through soft rollers. Glass bottles may receive glued paper labels that are brushed flat as the bottle turns. Cans usually arrive with their design already printed on the metal, so they move directly toward coating and packing after seaming and inspection. Coating equipment marks each container. Inkjet printers place production information onto the cap, bottle shoulder, label, can base, or glass surface. The code appears in a fraction of a second while the container remains in motion. Cold filling can create condensation on the outside. Air knives remove it. High-speed sheets of air strike the cap, shoulder, sidewall, seam, and base. Dry containers continue more reliably into packaging machinery. Dunkin' Donuts dough rings swell inside a humid proofing chamber before they ever touch hot oil. The rings enter the chamber, pale, flat, and soft. They ride on trays or open belts in steady rows. Warm air surrounds them from all sides. Moisture in the chamber keeps the surface flexible, while yeast activity expands the structure from within. The dough slowly rises, rounding at the edges and lifting away from its original cut shape. The proofing stage controls the lightness of the finished donut. The dough must inflate enough to float in the fryer, but not so much that it weakens and collapses. Temperature, humidity, and travel time are balanced, so every ring leaves with a soft skin, open internal cells, and enough strength to survive transfer. Before reaching this chamber, the rings are cut from a sheet of dough. The sheet moves beneath a rotary cutter fitted with circular blades. One blade cuts the outside edge of the donut. A smaller blade cuts the center hole. Each rotation presses through the sheet and releases another row of rings. The cutter must work cleanly. If the dough sticks, the ring stretches. If the blade is dull, the edge tears. A clean cut gives the donut a smooth outline, a centered hole, and a predictable expansion path during proofing. The surrounding dough web lifts away after cutting. It separates from the rings and moves onto a return belt. This recovered dough can be added back in controlled amounts, so the sheeting process remains efficient without overworking the next batch. The dough sheet itself is formed by rollers. Mixed dough enters the sheeting line as a thick, elastic mass. The first roller pair compresses it into a slab. Later rollers reduce the thickness step by step. The dough becomes broader, flatter, and more even with every pass. Side guides keep the sheet aligned. Scrapers remove dough from the roller surfaces. A light flour dusting system prevents sticking without covering the dough in excess powder. The final sheet thickness determines the weight and height of the raw donut. The dough starts in a mixer. Flour enters after sifting, which breaks up compacted lumps and removes oversized particles. Sugar, yeast, salt, milk solids, and leavening ingredients are dosed separately. Water flows in at a controlled temperature. Fat, egg ingredients, and flavor components enter through measured lines. The mixer begins at low speed. Flour absorbs water and turns from dry powder into damp clumps. The mass gathers around the mixing arms. As mixing continues, the dough stretches and folds repeatedly. It becomes smoother, warmer, and more elastic. The dough must be strong enough to trap gas in the proofer, but soft enough to fry into a tender crumb. Mixing time, hydration, fat level, and final temperature all shape this structure. When the dough reaches the target texture, it leaves the mixer and moves toward dividing. Dividing cuts the large dough mass into workable portions. These portions rest briefly before sheeting. Resting lets the dough relax, which helps it roll smoothly without shrinking back. The relaxed portions feed into the rollers and become the continuous sheet used for cutting. After proofing, the swollen rings move toward the fryer. Transfer equipment places them gently onto the oil surface. The dough is fragile at this point because it contains many gas cells. A rough drop would flatten the donut or distort the ring. The fryer carries the donuts in lanes through hot oil. As each ring touches the oil, steam forms at the surface. The lower side sets first. Bubbles race along the outer edge and through the center hole. The donut expands slightly as heat moves inward. A turning device flips the donut halfway through frying. The second side enters the oil and browns to match the first. The surface turns golden while the inside remains soft and airy. Oil temperature stays within a narrow range so the donut cooks through without becoming greasy or overdark. Loose crumbs are removed from the oil by filtration. This keeps dark fragments from sticking to later donuts. The fryer belt continues moving at a fixed speed, giving each donut the same exposure time. The fried donuts leave the oil on a draining conveyor. Excess oil falls through the mesh. The donuts remain hot, soft, and slightly fragile. Their crust is set, but the interior is still tender. From here, different varieties, split into separate finishing paths. Glazed donuts move forward while still warm. The glaze system uses a heated tank filled with sugar, water, and flavoring ingredients. Agitators keep the glaze smooth. A pump lifts it to an overhead trough where it falls as a continuous curtain. The warm donuts pass under the curtain. Glaze coats the top, slides down the sides, and flows around the inner ring. Extra glaze drains through the open conveyor and returns to the tank. The coating is thin at first and glossy, like a wet shell. The glazed donuts continue through a setting zone. Air moves over the surface. Moisture leaves the glaze. The coating tightens and becomes a smooth sugar layer that clings to the golden donut below. Chocolate frosted donuts follow a cooler path. They leave the fryer and cool longer before icing. If the donut is too hot, the chocolate coating becomes thin and runs. At the right temperature, the top surface receives a measured layer of icing. The donut passes beneath a coating head or touches a controlled icing surface. Chocolate icing spreads across the top and stops before fully covering the underside. The coating forms a smooth cap. It stays soft briefly, which allows toppings to attach. Sprinkle donuts move directly beneath a topping dispenser. Small colored pieces fall in a controlled shower. They strike the tacky icing and remain embedded. Loose sprinkles fall between the donuts and are collected away from the product path. Filled donuts begin as solid rounds, not rings. The cutter makes circular dough pieces without a center hole. These rounds proof into soft pillows and fry on both sides. After frying, they cool enough to receive filling without melting or leaking. The filling station uses narrow injection nozzles. Each nozzle enters the side of a donut. A pump delivers a measured amount of cream, jelly, custard, or flavored filling into the center. The filling spreads inside the soft crumb and slightly expands the donut. The nozzle withdraws, leaving a small entry mark. The filled donut may then be glazed, powdered, iced, or striped. Powdered donuts pass through a dusting chamber where fine sugar falls over the surface. The donut turns or moves through the powder stream, picking up an even coating. Excess powder drops through screens. Striped donuts pass beneath small decorating nozzles. Thin lines of icing cross the top while the donut moves on the belt. The nozzles release a steady flow, and the belt speed controls the spacing and length of the stripes. Cake donuts use a different batter system. Instead of yeast dough, a thicker batter is mixed with flour, sugar, fat, liquid ingredients, and chemical leavening. The batter is deposited directly into hot oil through a shaped depositor. As it fries, the batter expands and sets into a denser ring with a different crumb. The cake donut depositor controls the shape by extruding batter in a ring. The batter drops into the oil, floats, and fries. The outside becomes lightly crisp, while the inside sets into a moist cake texture. These donuts can be glazed, sugared, frosted, or coated after cooling. Donut holes can come from center cuts or separate depositing equipment. They fry as small, round pieces. Because they are smaller, they cook quickly and move through coating or glazing systems in large quantities. They may be tumbled in glaze, sugar, or powdered coatings before packing. After finishing, all donut varieties move through inspection. Cameras check color, shape, topping coverage, glaze thickness, icing placement, missing sprinkles, broken edges, and distorted centers. Filled donuts can be checked by weight to confirm the correct amount of filling. Defective pieces are rejected automatically. Accepted donuts are spaced by timing belts. The belts create separation so toppings do not smear. Guide rails organize the flow into lanes for packing. Different varieties may be routed into separate packing areas or assembled into assortments. Fanta production begins with a small orange flavor stream entering a much larger sweet syrup base. The flavor concentrate is intense, so it is not added by sight or by guess. It moves through a closed stainless steel line pushed by a metering pump that controls the dose. The syrup tank below it is already circulating. Its agitator pulls the liquid down through the center, throws it outward, and keeps the entire volume moving in a slow spiral. The sweet syrup starts with treated water. Before it reaches the tank, incoming water has already moved through filtration, activated carbon treatment, and polishing stages. Particles are removed. Unwanted taste and odor are reduced. The water becomes consistent enough to carry the same flavor strength in every batch. A measured volume of this treated water enters the syrup vessel. Sweetener follows through a dosing system. If dry sugar is used, the crystals fall into the moving water and dissolve gradually. If a liquid sweetener is used, it enters as a thicker stream and folds into the water as the agitator turns. The mixture becomes heavier as the sweetener dissolves. The surface changes from quick splashes to slower glossy waves. Controlled heat may help dissolve the sweetener completely. The liquid is not boiled. It is only warmed enough to form a smooth base with no gritty particles. The sweet base passes through fine filtration. Any undissolved material is caught before the syrup reaches the more sensitive mixing and filling equipment. Clean syrup protects pumps, flow meters, valves, and later filler nozzles. The filtered syrup enters the flavor building tank. This is where Fanta becomes different from a cola. Cola syrup is dark, caramel colored, and built around a compact, spice-like flavor system. Fanta syrup is bright, fruity, acidic, and usually designed around citrus character, color, and sometimes a slight clouded appearance. Orange flavor concentrate enters first or with the color system, depending on the formula. The stream is small, but it changes the whole tank. The syrup shifts from pale sweet liquid to a stronger orange base. The color looks deeper than the finished drink because dilution has not happened yet. Acid ingredients are added next. They create the sharp edge behind the sweetness. Citric acid is common in orange-flavored drinks because it gives a citrus-like bite. The acid is dissolved or added as a prepared solution. It enters below the surface and disappears into the moving syrup. Some orange soft drink formulas use an emulsion. Citrus oils do not naturally mix with water, so they are dispersed into extremely small droplets and held in suspension. This can give the drink a fuller, slightly cloudy look instead of perfect transparency. If an emulsion is part of the formula, mixing speed must be controlled carefully. The tank needs enough motion to distribute the droplets evenly, but not so much force that the droplet structure is damaged. The agitator works steadily, folding the syrup over itself without turning the vessel into violent foam. The finished syrup is now concentrated, orange, sweet, acidic, and strongly flavored. It is still not the final beverage. It is too dense and too powerful to drink. It must be diluted with treated water at a controlled ratio. The syrup flows toward the proportioning unit. A separate stream of treated water arrives from storage tanks. Both streams pass through flow meters. The proportioner compares them continuously and adjusts automatic valves in small movements. The machine keeps the blend ratio fixed. If syrup pressure changes, the valve corrects. If water flow increases, the syrup flow adjusts with it. The process prevents weak sections, overly strong sections, and color variation during a long production run. Inside the blending chamber, the concentrated syrup meets the water. The liquid becomes lighter and brighter. Its viscosity drops. The drink now has finished flavor strength, sweetness, color, and acidity. It is flat Fanta, not carbonated Fanta. The flat beverage moves into chilling equipment. It passes through a plate heat exchanger, flowing between thin stainless steel plates. A cold medium moves on the other side of the plates, pulling heat from the drink without mixing with it. The temperature drops quickly. Cold liquid absorbs carbon dioxide more easily than warm liquid. Cooling also prevents excessive foaming later, when the drink enters bottles or cans at high speed. The beverage may then pass through deaeration. In this stage, reduced pressure draws dissolved air out of the liquid. Tiny bubbles rise from the stream and separate. Removing excess air helps carbonation enter more cleanly and improves the way the drink behaves under pressure. Carbon dioxide enters through regulated gas lines. The gas is filtered and pressure controlled before it reaches the carbonator. Inside the carbonator, chilled Fanta and carbon dioxide meet under pressure. The gas dissolves into the liquid and creates the sparkling texture. From this point forward, the drink must remain enclosed. It travels through pressurized stainless steel, piping toward the filler. If the pressure dropped suddenly, carbon dioxide would escape as foam. While the beverage is being prepared, the containers are formed and cleaned. For PET bottles, production begins with preforms. A preform looks like a short, thick plastic tube with a finished threaded neck. The neck is already shaped with threads and a sealing surface. The body still needs to be expanded. Preforms enter an oven where infrared lamps heat the plastic. Each preform rotates while it moves through the oven, so the body warms evenly. The neck stays cooler because it must keep its exact dimensions for the cap. A heated preform enters a blow mold. The mold closes around it. A stretch rod pushes down through the center and pulls the plastic lengthwise. Compressed air then expands the softened plastic outward until it touches the chilled mold wall. The bottle shape appears instantly. The base forms into pressure-supporting feet. The shoulders curve outward. The label panel and grip contours set as the plastic cools against the mold. The mold opens, and the empty bottle exits by its neck ring. The bottles travel through air conveyors toward rinsing. They are light and thin, so air pushes them forward while rails support them by the neck. At the rinser, each bottle is inverted and cleaned inside with filtered air or treated rinse water. It drains, turns upright, and moves toward the filler. Can lines follow a different route? Empty aluminum cans arrive open at the top. They are already formed and printed. They enter an air rinser, turn upside down, receive a blast of filtered air, and return upright before filling. Glass bottle lines use formed bottles that pass through camera inspection before rinsing. The equipment checks the mouth, base, sidewall, and inside surface. Only clean, intact bottles continue to the filler. The filler is a rotating carousel. Containers enter through a star wheel that spaces them exactly. Each bottle or can is guided beneath a filling valve connected to the pressurized Fanta supply. Because the beverage is carbonated, filling is pressure controlled. A bottle seals against the valve. Pressure inside the container is balanced before liquid flow begins. This prevents a sudden eruption of foam. The valve opens. Orange Fanta flows into the container in a controlled stream. In a clear bottle, the liquid rises brightly from the base, carrying fine bubbles through the orange body. The fill level reaches the target point, and the valve closes. The filled container moves immediately to sealing. Plastic bottles pass under capping heads. Caps are sorted, oriented, and delivered down a chute. Each capping head picks up one cap, places it on the bottleneck, and tightens it to a set torque. The tamper band locks below the neck ring. Cans move to the seamer. A lid is placed on each filled can. Seaming rolls fold the lid curl and can flange together. The first operation hooks the metal. The second compresses it into a pressure-tight double seam. Ben & Jerry's ice cream mix enters the freezer barrel as a smooth liquid, then leaves as a thick, semi-frozen stream ready to catch chunks, swirls, and ribbons. The liquid mix is cold before it reaches the freezer. It has already been blended, pasteurized, homogenized, aged, and balanced for fat, sugar, milk solids, and stabilizers. At this point, it looks like heavy cream with dissolved sweetness and flavor. Inside the freezer barrel, rotating scraper blades drag across a chilled metal wall. A thin film of ice cream freezes against that wall almost instantly. The blades scrape it away before it becomes a solid sheet. The scraped crystals mix back into the liquid. More liquid touches the cold surface. More crystals form. The cycle repeats rapidly, building a creamy frozen structure instead of a hard block of ice. Air is added at the same time in controlled amounts. The air is broken into tiny bubbles and distributed through the mix. The liquid thickens as it transforms into soft ice cream. The freezer does not finish the product completely. It produces ice cream that is cold, dense, and pumpable. It must still be soft enough to accept cookie dough, brownies, chocolate pieces, nuts, caramel, fudge, fruit preparations, or other inclusions without breaking the machinery or crushing the pieces. Before this freezing step, the dairy base is built in stainless steel tanks. Cream, milk, skim milk solids, sugar, liquid sweeteners, stabilizers, and emulsifying ingredients are measured into the batch system. The ingredients enter by weight or flow rate. The tank agitator keeps the mixture moving so powders hydrate and liquids disperse. The dairy fat is one of the main structural elements. It gives richness and helps the frozen mix hold air. Sugar lowers the freezing point, so the final ice cream does not become rock hard at freezer temperatures. Milk solids add body. Stabilizers help control ice crystal growth and improve texture after hardening. Dry ingredients are added carefully. Sugar flows easily, but stabilizers can clump if they hit the liquid too quickly. A powder induction system pulls dry materials into a fast-moving stream of liquid, dispersing them before they form lumps. The tank gradually becomes uniform. Flavor bases may be added to the liquid mix at this stage. Vanilla, chocolate, coffee, fruit bases, or other liquid ingredients can be blended into the dairy stream. Cocoa ingredients require strong mixing because cocoa powder resists wetting and can form dark clumps if not dispersed properly. Chocolate mixes become darker and thicker as the cocoa hydrates. The blended mix is pumped through filters to remove undissolved particles before heat treatment. It then moves through a pasteurization system. In a continuous plate heat exchanger, the mix flows between thin stainless steel plates while hot water or steam-heated fluid moves on the other side. Heat transfers quickly through the metal, raising the mix temperature under controlled conditions. The hot mix passes through a holding tube for the required time. The flow rate and tube length control the exposure. After holding, the mix enters the cooling side of the exchanger, but first, it may pass through a homogenizer. Homogenization forces the hot mix through very small gaps under high pressure. The fat droplets are broken into smaller droplets and spread evenly through the liquid. This creates a smoother mix and improves body. Without this stage, fat could separate or create uneven texture in the finished ice cream. After homogenization, the mix is cooled quickly. Cold fluid on the opposite side of the heat exchanger pulls heat away. The mix exits cold and moves into aging tanks. These tanks hold it at low temperature for several hours. Slow agitators keep the mix uniform without whipping in air. During aging, fat crystallizes into a stable form. Stabilizers fully hydrate. The liquid becomes slightly thicker. This step prepares the mix for freezing. Aged mix whips better, freezes more smoothly, and carries inclusions more evenly. Inclusion preparation happens separately from the dairy mix. Cookie dough pieces are formed from dough, cut into small chunks and chilled or frozen so they remain distinct inside the ice cream. Brownies are baked in sheets, cooled, cut into cubes, and frozen or chilled to hold their shape. Chocolate chunks are formed, cooled, broken, or cut to size and screened so only the correct pieces continue. Nuts are roasted or prepared, cooled, and sized. Caramel cups, fudge flakes, candy pieces, or baked inclusions are held cold so they do not smear when added. Each inclusion must be strong enough to pass through the feeder, but tender enough to bite through in the final product. Swirls are prepared in heated or chilled holding systems depending on the ingredient. Fudge swirl is cooked into a thick, glossy sauce. Caramel is blended and held at a temperature where it flows but does not become watery. Fruit swirl contains fruit preparation, sugar, and stabilizing ingredients to keep the texture spoonable at frozen temperatures. These swirls do not enter the main mix tank. They are added after freezing, so they remain visible as ribbons rather than disappearing into the base. The timing is important. If a swirl enters too early, it blends into the ice cream and becomes a uniform color. If it enters too late, it may not distribute across the pint. The semi-frozen ice cream exits the continuous freezer and enters a fruit feeder or ingredient feeder. This machine meters solid inclusions into the moving ice cream stream. A hopper holds the chunks. An auger or pocketed rotor releases them at a controlled rate. The pieces fall into the ice cream and are folded through by the flow of the product. The feeder must avoid crushing the inclusions. Cookie dough chunks, brownie cubes, and chocolate pieces pass through wide openings and gentle mixing zones. The goal is not to grind them into crumbs. The goal is to suspend large, recognizable pieces throughout the dense, frozen base. The stream then moves toward the variegate or swirl injector. Thick sauce is pumped through dedicated lines and injected into the ice cream as it moves toward filling. The sauce enters in ribbons, streaks, or bands. It does not fully mix. It travels as separate colored paths inside the base. The product now contains frozen ice cream, air cells, ice crystals, fat structure, chunks, and swirl. It is soft enough to pump, but thick enough that pieces do not immediately sink. It reaches the pint filler through short, insulated piping. Empty Ben & Jerry's pint containers feed into the filling line. The paperboard tubs are stacked and separated one at a time. Each container is placed into a pocket or held beneath a filling nozzle. The filler must handle a product that is partly frozen and full of pieces. The nozzle deposits ice cream into the pint in a controlled pattern. It may fill from the bottom upward or use a rotating motion to distribute swirls and chunks. The product enters as a thick rope, folding into the container and building upward. Large inclusions settle into the base as the pint fills. The fill level is controlled by volume or weight. Too little product creates an underfilled pint. Too much product can interfere with lidding or create product on the rim. The filler cuts off cleanly so the rim remains clear. Some flavors need extra topping or a core style addition. In those formats, the filler may deposit part of the ice cream, inject a central stream of caramel, fudge, cookie butter, or another component, then finish with more ice cream. The core must remain centered and thick enough to stay visible when scooped. After filling, a lid is placed on the pint. Lids feed from a magazine or hopper, separate one at a time, and press onto the rim. The container now holds soft ice cream that is shaped but not yet fully hardened. The pints pass through check weighing. The machine weighs each container and rejects any pint outside tolerance. Vision systems inspect lid placement, container condition, print orientation, and visible rim contamination. The filled pints move quickly toward hardening. This is where the soft, frozen product becomes stable enough for storage and distribution. The pints enter a hardening tunnel or spiral freezer. Very cold air moves at high speed around the containers. Heat leaves the pint from the outside inward. The ice cream firms against the container wall first. The center hardens more slowly. The air movement must be strong because pints are thick. Packages, and the product contains chunks and swirls that affect how heat transfers. Corny chocolate production begins with a hot binder syrup forming inside a heated mixing vessel. Sugar syrup, glucose syrup, honey-like syrup components, fat, cocoa ingredients, and flavoring are measured into the tank. The liquid warms as the agitator turns. At first, the mixture is thin and separate in places. As heat spreads through the vessel, the sugars dissolve, the fat disperses, and the binder becomes glossy and uniform. This binder is the part that turns loose grains into a bar. It must be sticky enough to hold cereal pieces together, but not so fluid that it runs away from the mixture. It also must cool into a chewy, stable structure. The tank controls temperature and mixing speed so the syrup stays pumpable without becoming too dark or too thick. Dry cereal ingredients are prepared on a separate line. Rolled oats, crisped rice, wheat flakes, corn flakes, puffed grains, and small cereal clusters can be combined depending on the specific bar formula. Each ingredient moves through its own feeder before joining the main dry blend. The dry ingredients pass through screens before mixing. Oversized clumps are removed. Fine dust and broken fragments can be reduced so the bar does not become powdery. The goal is a mixture with visible grain pieces and enough small particles to fill spaces between larger flakes. Chocolate chips or cocoa-flavored pieces may be added to the dry stream. These pieces must be cool and firm before they enter the mix. If they are too warm, they smear into the cereal instead of remaining as separate inclusions. The feeding system meters them gently so they do not break apart before forming. The cereal blend enters a large horizontal mixer. The paddles rotate slowly, lifting and folding the light grains without crushing them. The hot binder syrup is pumped in through several nozzles, spreading across the moving bed of cereal. The syrup lands as thin ribbons. The mixer turns the grains through the syrup again and again. Dry flakes become glossy. Puffed pieces catch the binder in their rough surfaces. Small grains settle into gaps between larger pieces. The mixture changes from loose cereal into a sticky, connected mass. The timing of this stage is critical. Too little mixing leaves dry pockets that fall apart later. Too much mixing breaks flakes and compresses the texture. The mixer must coat the grains evenly while preserving their shapes. Once the cereal mass reaches the right consistency, it discharges onto a forming conveyor. The mixture is warm, sticky, and uneven at first. It drops as a thick layer and passes beneath spreading rollers. Side guides contain the edges so the layer stays at the correct width. The forming section compresses the mass into a continuous slab. A first roller spreads it. A second roller levels it. A calibrated compression belt presses from above, while the conveyor supports it from below. The grains lock together as the binder fills the spaces between them. The slab thickness determines the final bar height. If the slab is too thin, the bar becomes brittle and flat. If it is too thick, the center may not cool evenly. The forming equipment holds the layer at a steady height across the entire width. The top surface is textured by the grains, but the slab must still be even enough for cutting and coating. The rollers do not grind the cereal smooth. They press it just enough to bind the structure while leaving visible oat flakes, puffed grains, and crisp pieces. The warm slab moves into a cooling tunnel. Cold air passes over the top and through the conveyor area. The binder begins to firm. The mass changes from soft and sticky to flexible and stable. It must cool enough to cut cleanly without cracking. Inside the slab, the syrup sets around the grains. Each piece becomes part of a larger network. The bar texture depends on this balance. The binder stays chewy, while the cereal pieces remain crisp or lightly crunchy. After cooling, the slab reaches the cutting section. Long circular knives slice it lengthwise into continuous strips. The blades pass through grains and binder, leaving straight edges. The strips separate slightly as they move forward. A cross cutter then divides the strips into individual bar lengths. The blade moves in rhythm with the conveyor. Each downward cut creates another bar. The cut must be fast and clean, because slow pressure would drag the sticky binder and deform the edge. The separated bars now have their cereal structure, but the chocolate part still needs to be added. Chocolate coating is prepared in a separate system. Cocoa ingredients, sugar, milk powder, cocoa butter, or coating fats, and flavor components are mixed into a smooth chocolate mass. The mixture passes through refining equipment to reduce particle size and remove grittiness. The chocolate then moves through conching or intensive mixing. The mass becomes smoother and more fluid. Fat coats the dry particles. The chocolate develops the flow needed for coating the bar evenly. Before coating, the chocolate is tempered or conditioned depending on the coating type. Temperature is adjusted so the chocolate sets with the correct firmness and surface finish. The coating must remain liquid at the enrober but become solid quickly after cooling. Corny chocolate bars can be coated in several ways. Some versions receive chocolate on the bottom only. Others are dipped, striped, or fully enrobed. For a bottom-coated bar, the cereal bar travels across a chocolate bed or roller that applies a layer to the underside. The underside touches the liquid chocolate and picks up a smooth base layer. Excess coating is scraped or controlled by rollers so the layer is even. The chocolate base helps hold crumbs, adds flavor, and creates a clean surface against the wrapper. For a fully coated format, the bars enter an enrober. They ride on a wire mesh belt under a falling curtain of chocolate. The chocolate flows over the top, down the sides, and around the cut edges. A lower coating stream covers the underside through the mesh. Excess chocolate drains away and returns to the circulation tank. Air blowers remove extra coating from the top and sides. The airflow smooths the surface and controls thickness. The coating must cover the uneven cereal edges without becoming too heavy. For striped bars, the main chocolate layer sets slightly before thin nozzles apply lines across the top. The nozzles move, or the bars pass beneath them at a controlled speed, creating repeated chocolate stripes. These lines sit on the surface as a decorative and flavor layer. After coating, the bars enter a cooling tunnel. Chilled air flows around them while they move forward. The chocolate changes from liquid to solid. The surface firms first, then the full coating stabilizes. The cereal center remains intact inside the shell or beneath the base layer. Cooling must be gentle enough to avoid cracking, but strong enough to set the chocolate before wrapping. If the coating is still soft, it will smear on belts and film. If it is cooled too aggressively, the surface can lose its smooth finish. At the tunnel exit, the bars pass through inspection. Cameras check length, width, coating coverage, broken edges, exposed cereal patches, chocolate smears, and missing stripes. Metal detectors scan the product stream. Bars outside the programmed limits are rejected automatically. Accepted bars move into the wrapping section. Timing belts separate them into equal gaps. The bars align lengthwise, so each one enters the wrapper in the correct position. Printed film unwinds from a roll. Tension rollers keep the film smooth. Registration sensors read printed marks so the wrapper design lines up with the bar. The film folds around the product through a forming box. A longitudinal seal closes along the underside or back of the wrapper. Heated sealing wheels press the film layers together. Cross-seal jaws close the front and back ends of each pack, sealing and cutting one wrapped bar from the continuous film. The wrapper protects the cereal texture from moisture and keeps the chocolate surface clean. It must sit close to the bar without crushing the grains or marking the coating. Wrapped bars pass through check weighers. A short bar, broken bar, or missing product produces a weight outside the target range. Vision systems inspect seal quality, film position, print alignment, and code placement. Defective packs are diverted from the line. Maltesers begin with a brittle malt center expanding into a tiny honeycomb sphere. The center is the part that makes the product different from an ordinary chocolate ball. It is light, crisp, and porous, with a dry snap inside a smooth milk chocolate shell. The manufacturing line is designed to build that contrast in stages. First the malted center, then the rounded shape, then the chocolate layers, then polishing, cooling, weighing, bagging, and final packing. The malt center starts as a cooked mixture. Malt extract, sugar, glucose syrup, milk ingredients, and other dry components are measured into a controlled batching system. The ingredients enter mixing vessels, where heat and agitation turn them into a thick syrup. The syrup must be uniform before it can be aerated and expanded. Malt extract gives the center its toasted, cereal-like flavor. It blends into the sugar system as the liquid warms. The mixture becomes darker, thicker, and more elastic. Agitators keep it moving so the sugars do not settle or burn against heated surfaces. The syrup then moves into a cooking stage. Heat drives off moisture and concentrates the sugars. The liquid becomes more viscous as water evaporates. Its temperature and solids level must reach the correct point, because the final texture depends on how the sugar structure sets after expansion. At this stage, the mixture is still dense. It has flavor, sweetness, and malt character, but it does not yet contain the light honeycomb structure. That structure forms when the cooked mass is expanded. Gas generation or aeration creates tiny cavities inside the hot sugar malt mixture. The expanding gas pushes through the softened mass, forming a network of bubbles. The bubbles stretch the syrup into thin walls. As the mixture cools, those walls harden into a crisp, porous structure. The material changes quickly. A heavy syrup becomes a lighter foam-like mass. It is not soft like whipped cream. It is a hot sugar structure full of trapped voids. When it sets, it becomes brittle and dry. The expanded malt mass is cooled and broken down into smaller pieces. It may be formed into rough pellets, cut, screened, or milled into controlled fragments before shaping. The goal is to create center pieces that can be rounded into small balls of consistent size. The pieces pass through sizing equipment. Screens remove fines and oversized fragments. Airflow can pull away light dust. The accepted pieces move into rounding equipment. The centers tumble inside rotating pans or drums, where their edges are gradually worn down. Rounding is slow and mechanical. The rough pieces roll against each other and against the drum surface. Corners break away. Flat faces soften. Each piece becomes closer to a sphere. Small additions of binding material or syrup may help the particles build a smoother surface as they tumble. The center does not need to be perfectly polished yet. It only needs the right size, shape, and strength for chocolate coating. If the center is too rough, the chocolate shell becomes uneven. If it is too fragile, it will break during panning. If it is too dense, the final bite loses the light Malteser's texture. The rounded malt centers move through a drying and conditioning stage. Warm air reduces surface moisture and stabilizes the texture. The centers must be dry before chocolate is applied. Moisture would interfere with coating and could make the chocolate grip unevenly. Before coating, the centers are inspected and classified. Small broken pieces are removed. Oversized centers are separated. Dust is screened away. A clean, dry stream of malt balls then moves toward the chocolate panning area. Milk chocolate is prepared in a separate system. Cocoa ingredients, milk powder, sugar, cocoa butter, and vegetable fat or other formula components are mixed and refined. The mixture passes through rollers that grind the particles smaller. Refining gives the chocolate a smoother mouthfeel by reducing the size of sugar and cocoa particles. After refining, the chocolate is conched. In conching machines, heavy mixing arms continuously move the chocolate for a controlled time. The process smooths the texture, distributes fat around the dry particles, and develops the final flavor. The chocolate becomes glossy, fluid, and uniform. The chocolate must then be tempered. Tempering controls how the fat crystals form. The chocolate is cooled and gently reheated through a precise temperature curve. This creates stable crystals that help the coating set with a clean finish. Proper tempering gives the shell firmness and reduces dullness or soft texture. The malt centers enter coating pans. These are large rotating drums, angled so the centers tumble continuously. A measured amount of tempered milk chocolate is sprayed or ladled onto the moving centers. The chocolate touches the dry malt balls and spreads as they roll. The first layer is thin. It seals the porous center and creates a smoother surface for later layers. The centers continue tumbling while cool air passes through the pan. The chocolate sets around each piece. Once the layer is firm enough, another small addition of chocolate is applied. The coating builds gradually. Maltesers are not coated with one heavy pour of chocolate. The shell forms through repeated thin layers. Each layer must spread, set, and bond before the next layer arrives. This creates a rounded, even chocolate covering without flooding the centers or joining them together. The sound inside the pan changes as the shell thickens. At first, the centers make a dry rattling sound. As chocolate builds, the movement becomes softer and heavier. The pieces roll over one another with a smoother, duller sound. The pan speed, air temperature, chocolate temperature, and addition rate all control the shell. If chocolate is added too quickly, pieces stick together. If air is too cold, the coating can set before it spreads. If air is too warm, the surface stays tacky. The machine balances movement, temperature, and timing until each ball reaches the correct size. After the main chocolate coating is built, the pieces continue tumbling to smooth the surface. Small ridges are evened out by rotation. The shell becomes more uniform with every turn. The pieces are now recognizable as Maltesers, but they still need finishing. A polishing stage may apply a very thin finishing layer. The pieces tumble while a glazing or polishing material is added in tiny amounts. This gives the chocolate surface a smooth, lightly glossy appearance and helps reduce scuffing during packaging. The finished pieces then move into cooling. They travel through a cooling tunnel or controlled room where air removes heat from the shell. The chocolate firms fully. The coating becomes stable enough for weighing, conveying, and bagging. After cooling, the Maltesers pass through inspection. Screens remove broken pieces, dust, and double pieces stuck together. Metal detection checks the product stream. Optical systems can detect unusual shapes, exposed centers, dull patches, or oversized clusters. Rejected pieces are separated from the main flow. The accepted pieces move into holding hoppers above the packaging line. The hoppers are designed to keep the chocolate pieces moving gently. Sharp drops are avoided because the coating can scuff or chip. Controlled gates feed the product into weighing systems. Multi-head weighers portion the Maltesers into exact amounts. The pieces fall into small weighing buckets. The control system selects the best combination of buckets to reach the target weight. Gates open and the measured amount drops into the bagging machine. For small bags, packaging film unwinds from a roll. The film passes over a forming collar and wraps into a tube. A vertical heat seal closes the back seam. The weighed Maltesers drop into the open tube. Horizontal sealing jaws close the bottom and top seals, forming individual bags. The sealed bag passes under a coder. Production information is printed onto the film. The bag then moves through check weighing. Any underweight or overweight pack is rejected automatically. For boxed formats, the pieces may be weighed into a bag first, then inserted into a carton. Flat paperboard blanks are opened into box shapes. The filled inner pack slides inside. Folding rails close the flaps. Adhesive or locking tabs hold the carton shut. Twix begins as a long sheet of biscuit dough moving toward a cutting line. The dough is built to become a crisp base. It must be strong enough to carry caramel, but light enough to snap cleanly under the chocolate shell. The process starts with flour, sugar, fat, leavening ingredients, salt, and water entering a controlled mixing system. Dry ingredients are weighed first. Flour flows from storage bins through enclosed conveyors. Sugar and smaller powders are added through separate dosing units. Each ingredient passes into a mixer in measured amounts. The mixer does not simply stir the powders. It builds a dough with the right texture for sheeting, cutting, baking, and coating. Fat is added to create the short, crumbly biscuit texture. It coats part of the flour and limits gluten development. This is what helps the biscuit break cleanly instead of becoming chewy. Water enters slowly, just enough to bind the dry ingredients. The mixer blades fold, press, and turn the mass until it becomes a firm dough. The dough exits the mixer in heavy pieces. It is fed into a hopper above a sheeting machine. Large rollers pull the dough downward and compress it into a thick sheet. The sheet passes through more rollers. each pair reducing the thickness. The surface becomes smoother with every pass. The dough sheet must reach a precise thickness. If it is too thick, the biscuit will bake slowly and make the bar heavy. If it is too thin, it can crack under the caramel layer. The sheeter controls the height with adjustable roll gaps. Once the sheet is even, it moves under cutting rollers. The rollers score and cut the dough into long, narrow biscuit fingers. Small holes may be docked into the surface. Docking lets steam escape during baking and helps prevent the biscuit from puffing unevenly. The shaped dough pieces transfer onto an oven band. The band moves continuously through a long baking tunnel. Heat surrounds the dough from above and below. Moisture begins leaving the biscuit. The surface firms first, then the center dries and sets. Inside the oven, the dough changes from pale and soft to golden and crisp. The fat melts, water evaporates, and the structure becomes rigid. The biscuit pieces shrink slightly as they bake. Their edges sharpen, and the surface develops a light toasted color. The oven has different temperature zones. The first zone sets the shape. The middle zones drive off moisture. The final zones finish the color and texture. The goal is a biscuit that is dry, crisp, and strong enough for high-speed handling. The baked biscuit fingers leave the oven and enter a cooling section. Air flows over and under the pieces. Cooling is important because caramel cannot be applied properly to hot biscuits. If the biscuit is too warm, the caramel may spread too much or soften the structure. The cooled biscuits travel in straight lanes. Conveyor guides align them precisely. The next layer is caramel. Caramel is prepared in a separate cooking system. Sugar, glucose syrup, milk ingredients, fat, and water are mixed in heated vessels. The mixture starts as a pale liquid. As it cooks, water evaporates and the sugars concentrate. The liquid thickens and develops a smooth, stretchy body. The caramel must be cooked to a very specific texture. It cannot be too runny, or it will flow off the biscuit. It cannot be too firm, or it will not deposit evenly. The finished caramel must hold its shape as a layer, but remain soft enough to bite through. After cooking, the caramel is cooled to a controlled depositing temperature. It remains warm and pumpable. Pipes carry it to the depositor above the biscuit lanes. The depositor contains nozzles matched to the spacing of the biscuits. As each biscuit passes underneath, a ribbon of caramel is laid along the top. The caramel lands as a smooth strip, following the length of the biscuit. The depositor times each flow so the caramel starts and stops at the right point. It must not hang over the ends too far, because excess caramel can interfere with chocolate coating. The caramel-topped biscuits continue forward. Cooling air firms the caramel surface. The layer becomes stable enough to move, but it remains soft inside. The product now has the basic Twix structure: biscuit base and caramel top. Some lines form the biscuit and caramel as long continuous strips before cutting. In that version, caramel is deposited onto long biscuit slabs. The slabs then pass through slitting and guillotine cutting systems that divide them into individual bars. The cutting blades must pass cleanly through caramel and biscuit without dragging the layers out of position. The formed bars are spaced apart before chocolate coating. Correct spacing matters because the enrober must cover every side without bars touching each other. Vibrating conveyors and timing belts create even gaps between the pieces. Milk chocolate is prepared in another part of the factory. Cocoa ingredients, sugar, milk powder, cocoa butter, and fats are blended into a chocolate mass. The mixture is refined through rollers that reduce particle size. This gives the chocolate a smooth texture instead of a gritty one. The refined chocolate is conched. Heavy mixing arms move the chocolate for a controlled time. The mass becomes smoother, more fluid, and more uniform. The fat coats the dry particles evenly. The chocolate develops the proper flow for coating. Before it can cover the bars, the the chocolate is tempered. Tempering controls the crystal structure of the cocoa butter. The chocolate is cooled and warmed through a precise temperature curve. Stable crystals form, allowing the coating to set with a firm surface and clean snap. The Twix bars enter the enrober on a wire mesh belt. A curtain of tempered milk chocolate falls from above. Each bar passes through the curtain and chocolate flows over the caramel top, down the sides, and around the biscuit edges. At the same time, chocolate is applied from below. The mesh belt allows chocolate to coat the underside. The bar becomes fully covered. Excess chocolate drains through the belt and returns to the tempering system. After the curtain, the bars pass under air blowers. These blowers remove extra chocolate from the top and sides. The airflow smooths the coating and controls shell thickness. Too much chocolate would make the bar heavy and uneven. Too little would expose biscuit or caramel. The coated bars then pass over a vibrating section. The vibration helps remove trapped air bubbles and evens the chocolate surface. The shell becomes smoother as the bar continues forward. The surface pattern forms as the chocolate settles. Twix bars often have a slight ripple or flow texture on top because the chocolate curtain, airflow, and movement shape the coating before it sets. The ridges are not carved after cooling. They form while the chocolate is still fluid. The bars enter a cooling tunnel. Inside, chilled air circulates around them. The chocolate shell begins to crystallize and harden. Cooling must be controlled carefully. If it is too fast, the coating can become dull or crack. If it is too slow, the chocolate may remain soft and mark during wrapping. As the bars move through the tunnel, the shell changes from glossy liquid to firm chocolate. The caramel stays enclosed. The biscuit remains dry because the coating seals it from the outside. At the end of cooling, the bars leave the tunnel fully set. They pass through inspection. Cameras check shape, size, coating coverage, and surface defects. Metal detectors scan the product stream. Bars with exposed biscuit, missing chocolate, broken edges, or distorted caramel are rejected automatically. Accepted bars move toward wrapping. Twix bars are usually packed as paired fingers or single bars depending on the format. Lane systems align the bars and bring them into the required grouping pattern. For a twin pack, 2 bars are placed side by side with controlled spacing. The wrapper begins as a roll of printed film. The film unwinds and passes through rollers that control tension. It moves around a forming box, where it wraps around the bar or bar pair. The product enters the film tube in perfect timing with the print registration. A longitudinal seal closes the film along the back or underside. Heated sealing wheels or jaws press the film layers together. Then cross-seal jaws close the ends of each pack. The jaws seal and cut at the same time, separating one wrapped pack from the next. Bounty begins with shredded coconut being turned into a compact, moist center. The coconut is the main structure of the bar. It does not start as a smooth paste. It starts as small white flakes with a fibrous texture. Each flake must be hydrated, sweetened, bound together, shaped into bars, covered with chocolate, cooled, wrapped, and packed without losing the soft coconut bite inside. The coconut arrives in dry, shredded form. It is stored in ingredient bins or bags before feeding into the mixing area. The flakes are light and irregular. Some pieces are longer, some are finer. The production system controls the blend, so the finished center has an even texture. Before mixing, the coconut may pass through screens. Oversized pieces are separated. Very fine dust can be reduced. The goal is not to make the coconut perfectly uniform, but to keep the texture consistent enough for forming. The center must hold together, but it still needs visible coconut fibers. A syrup phase is prepared separately. Sugar, glucose syrup, water, and milk-based ingredients are measured into heated vessels. The liquid warms as agitators turn. The sugar dissolves into the water and syrup base. The mixture becomes glossy and smooth. This syrup is the binder. It gives the coconut center sweetness, moisture, and shape retention. It must be thick enough to hold the flakes together, but not so thick that it forms a hard candy texture. The final bar needs a soft pull when bitten, not a brittle snap. Fat ingredients are added into the warm syrup system. They help create a creamy texture and reduce dryness in the coconut mass. The warm liquid becomes richer and more opaque as the fat disperses. Mixing keeps the binder even so no area becomes greasy or thin. The syrup is cooked to a controlled solids level. Water evaporates as heat continues. The mixture thickens slightly. The factory does not rely on appearance alone. Temperature, time, and flow controls keep the binder within the correct range. The shredded coconut then enters a heavy-duty mixer. The dry flakes drop into the bowl or continuous mixing chamber. The warm binder is added gradually. The mixer turns slowly at first, folding syrup into the coconut. Then the paddles increase their work, pressing and lifting the mass. The texture changes quickly. Dry flakes become damp. Loose coconut turns into a cohesive mixture. The white fibers become glossy as the binder coats them. The mass begins to clump, but the mixer prevents large lumps from forming. This is one of the most important stages in bounty production. If the coconut receives too little binder, the center will crumble. If it receives too much, the bar will feel sticky and heavy. If mixing is too rough, the flakes break down and the texture becomes pasty. The machine must combine the ingredients while preserving the fibrous coconut structure. The finished coconut mass is warm, moist, and thick. It cannot be poured like liquid. It must be pressed, extruded, or sheeted into the correct bar shape. The mass feeds into a forming machine. In one method, it is forced through a wide rectangular die as a continuous slab. Rollers or belts control the height and width. The surface is leveled as the coconut sheet moves forward. The sheet must be dense enough to stay together, but not compressed so hard that the center loses its softness. Another method forms the coconut mass into long ropes. The mixture passes through shaped openings, producing continuous bars with rounded edges. The ropes move on conveyors while cutting blades divide them into individual lengths. The forming system gives the center its basic profile. A bounty center is not flat like a biscuit base. It is thick, soft, and slightly rounded. The shape matters because the chocolate coating must flow over it evenly. Sharp corners would make thin chocolate spots. Smooth edges help the shell cover the bar completely. After forming, the coconut centers move into a cooling or setting section. Cool air firms the binder. The bars become easier to handle. The center does not become hard. It simply gains enough structure to survive transfer, spacing, and chocolate coating. The bars pass through alignment guides. They must travel in straight lanes with equal gaps. Uneven spacing would cause problems in the enrober. Two bars touching each other could become stuck together by chocolate. A bar out of position could miss part of the coating curtain. Chocolate preparation runs separately from the coconut line. Cocoa ingredients, sugar, milk powder for milk. Chocolate versions, cocoa butter, and other fats are combined into a chocolate mass. The ingredients are mixed until they form a thick paste. This paste passes through refining rollers that grind the sugar and cocoa particles down to a fine size. Refining changes the texture from gritty to smooth. The refined chocolate then moves into conching equipment. Large mixing arms or rollers work the chocolate for a controlled period. The mass becomes smoother and more fluid as fat coats the dry particles. Heat and movement develop the final flow behavior needed for coating. Before the chocolate can cover the coconut bars, it must be tempered. Tempering controls the cocoa butter crystals. The chocolate is cooled, stirred, and gently warmed through a precise sequence. This creates stable crystals that allow the shell to set firm, smooth, and glossy. The tempered chocolate is pumped to the enrober. The coconut centers approach on a wire mesh belt. The belt carries them beneath a falling curtain of chocolate. As each center passes through the curtain, chocolate pours over the top and runs down the sides. At the same time, chocolate coats the underside. The mesh belt allows chocolate to rise or be applied from below, so the coconut center is sealed all around. Excess chocolate drains through the belt and returns to the circulation system. The coating is not finished immediately after the curtain. The bars pass under controlled air blowers. These blowers remove excess chocolate and smooth the shell. They also help define the final coating thickness. The airflow must be strong enough to even the surface, but not so strong that it exposes coconut. The soft shape of the coconut center affects how the chocolate moves. The coating flows more easily over rounded sides than over sharp corners. It gathers slightly at the base before excess drains away. The wire belt supports the bar while leaving only fine contact marks underneath. The coated bars may pass over a vibrating section. The vibration releases trapped air bubbles and helps chocolate settle evenly. Small ripples smooth out as the bar continues forward. The shell becomes continuous around the coconut core. Some bounty formats are twin bars. In those lines, centers may be formed and coated as individual fingers, then later paired inside the wrapper. The spacing system keeps the fingers separated until the wrapping stage. Each piece must have its own complete chocolate shell before pairing. The coated bars enter a cooling tunnel. Chilled air flows around them as they move slowly through the enclosed space. The chocolate begins to crystallize. The liquid shine becomes a firmer surface. The shell sets without melting the coconut center or drawing moisture outward. Cooling must be balanced. If the tunnel is too cold, chocolate can contract too sharply and crack. If cooling is too slow, the bars may mark or deform before wrapping. The line controls air temperature, humidity, belt speed, and residence time. Hard candy only has two useful states on a lollipop line: fluid enough to be shaped and glassy enough to hold its shape. Chupa Chups style production is built to push the candy through that transition at the exact moment a stick is inserted and locked, then isolate the finished piece from humidity so it never leaves the glassy state. The most reliable way to understand the factory is to start at the forming wheel, because every upstream system exists to feed that wheel at a stable rhythm. The forming wheel is an indexed machine with cavities that open, receive a dose of hot candy, accept a stick, close to shape, then release the lollipop. Its speed is fixed by output targets, so the candy mass must arrive at the depositor at the correct temperature and viscosity, and sticks must arrive at the inserter in the correct orientation and at the correct moment. Stick handling runs continuously. Sticks are cut to length if not pre-cut, then screened to remove splinters. A deburring or air cleaning stage strips dust because dust at the interface weakens bonding and creates voids. Sticks are then singulated into individual lanes. Singulation is a mechanical sorting problem. Sticks are light and can overlap, so feeders rely on vibration, step conveyors, and guide rails to separate them. Orientation is enforced, so the same end enters the candy each time. The stick feed ends at a pick-and-place head or pusher that inserts the stick into the cavity at a fixed depth. Depth stops are mechanical, so insertion depth remains consistent even if stick length varies slightly. Depth matters because too shallow reduces pull strength, and too deep can create internal stress rings that lead to cracking. While sticks are being fed, the candy mass is being prepared as a concentrated syrup that will set into a clear glass. Sugar is stored dry and screened, so clumps do not enter dissolving. Water is filtered and tempered because inlet temperature affects dissolution speed and cook stability. Glucose syrup is held in jacketed tanks, so viscosity stays stable for pumping, and it functions as a crystallization control ingredient. These streams combine in a dissolver, where heat and agitation create a clear solution. The target is full dissolution with no visible grains, because undissolved grains become nucleation sites that can trigger graining later, making the candy cloudy and brittle in an unpredictable way. Concentration is performed rapidly to reach hard candy solids. In a continuous system, the clear syrup is pumped through heated coils under pressure, allowing temperature to rise quickly without boiling inside the tube. A flash chamber then reduces pressure so a portion of water instantly vaporizes and exits as steam. This flash step tightens final moisture and also reduces thermal damage because water removal occurs at a lower effective temperature than extended open boiling. Final moisture content is the main structural setting. Too much moisture yields candy that stays tacky and softens quickly. Too little moisture yields candy that becomes overly brittle and cracks at the stick interface during cooling or later handling. Immediately after concentration, the mass enters a controlled cooling section. The aim is to bring the mass to a forming temperature that is still fluid enough to be deposited and shaped, but not so hot that it degrades flavor and not so cool that it begins to set in pipes. Heat exchangers and jacketed manifolds manage this temperature precisely. At this stage, additives are introduced because many flavors contain volatile compounds that would be stripped or damaged at peak cooking temperatures. Color is prepared as concentrated solutions or dispersions and filtered so no particles clog injectors or create specks. Flavor is metered by precision pumps into the candy stream. Injection is placed after the main heat load so aromatics are preserved. Acid can be introduced as a solution if the recipe calls for a sharper profile, but acid timing is controlled because acid accelerates sucrose inversion at high temperature, which changes viscosity and long-term stickiness. Mixing after injection is done with static mixers or low-shear mixing manifolds that fold the flow and eliminate streaks without entraining air. Air entrapment is undesirable because bubbles create weak zones and can appear as surface pits once the candy cools. The candy mass then feeds the depositor at the forming wheel. The depositor meters a precise amount into each cavity. Portion volume directly sets lollipop size and weight. Metering is done by piston pumps or gear pumps synchronized to the wheel index. Dose accuracy matters because a low fill yields thin spots and poor stick anchoring, while an overfill creates flash that must be trimmed and increases wrapper puncture risk. The cavity receives the candy dose first or simultaneously with stick insertion depending on machine design. In one approach, the cavity is partially filled, then the stick is inserted, then a second small dose tops off and the cavity closes. In another approach, the cavity closes on a measured candy slug and the stick is driven into it. The common requirement is that candy must be plastic at the moment the stick enters, so the candy wets the stick surface and bonds as it cools. Shaping occurs when the cavity closes. The closing motion forces candy into the spherical geometry and expels trapped air. Venting channels can allow small air pockets to escape so they do not remain as bubbles. Cavity surface finish is polished, so the candy skin releases cleanly. Cavity temperature is managed so candy does not stick or smear. If cavities are too cold, the candy skin sets instantly and can trap air. If cavities are too warm, the candy remains tacky and can deform during demolding. The machine therefore maintains a stable mold temperature through internal circulation. As the formed lollipop exits the cavity, it is still hot enough that the interior is not fully glassy. It immediately enters a cooling system that locks structure. Cooling is staged. The first stage sets the outer surface quickly so the shape stops flowing. This can be done with cool, dry air directed at the candy surfaces. The second stage brings the core temperature down so the entire mass crosses into the glass state. Cooling rate must be controlled because excessive thermal gradients create stress. Stress tends to concentrate around the stick insertion zone because the stick acts as a rigid inclusion and the candy contracts around it. If the outer layer contracts much faster than the inner, microcracks can form. These cracks may be invisible initially, but can propagate during shipping or when humidity changes. Humidity control in cooling is essential. Hard candy absorbs moisture from air. If cooling air is humid, a thin moisture film can form on the warm candy surface. This film dissolves sugar at the surface and then recrystallizes as a rough haze, reducing gloss and increasing stickiness. Cooling tunnels therefore use dry air. Some lines control dew point directly, keeping dew point low enough that condensation cannot form on the candy at any point in the tunnel. Once cooled to handling temperature, lollipops are demolded or released from the forming wheel and transferred to conveyors. Transfer points are designed to avoid impact at the candy head because the surface can still mark if it is too warm. Guides support sticks rather than candy heads because contacting the head can create flat spots. The lollipops pass through inspection and rejection systems. Vision systems can detect off-center sticks, incomplete fill, surface bubbles, and flash around seams. Weight checks can detect underfill and overfill. Reject mechanisms remove defective pieces before wrapping because wrapping a defective piece wastes film and creates downstream jams. Twizzlers are manufactured by converting a cooked sweet base into a plastic, elastic candy dough, shaping that dough continuously through extrusion, setting texture through staged drying and cooling, then cutting and wrapping so the ropes stay chewy and separate without sticking. The most useful place to start is the cutter, because the cutter reveals whether the upstream dough has the right cohesion and whether the rope has been set enough to hold its geometry. If the rope tears at the cut, the dough is underhydrated or too cold. If it smears and strings, the dough is too warm or too wet. The factory therefore tunes the entire process to deliver an extrudate that behaves predictably at the knife. Upstream of the cutter, the rope travels through setting tunnels that control moisture and temperature. Those tunnels are what convert an extruded ribbon into a stable Twizzler's rope with a uniform chew. The rope exits the die warm and pliable, and its interior still contains enough water to make it sticky if packaged immediately. The setting tunnel removes a measured amount of moisture while allowing the matrix to equilibrate so the surface becomes dry enough to handle, yet the core remains chewy. Air temperature, humidity, and velocity are balanced to avoid case hardening. Case hardening creates a tough outer shell and a soft interior, which leads to cracking during bending and an uneven bite. Staged zones, warmer early zones, and gentler later zones reduce that risk. Before the rope ever reaches those tunnels, the line creates the candy dough in a cooker and mixer system designed for high solids. Sugar and glucose syrup are staged as the main carbohydrate system. Granulated sugar is screened to remove clumps and dust because clumps dissolve unevenly and dust can scorch at hot surfaces. Glucose syrup is held in jacketed tanks so viscosity stays stable for metering. Water is filtered and tempered because inlet temperature shifts dissolution and cook stability. Starch and other structure-building solids are held dry and fed accurately because their hydration rate determines dough firmness later. Cooking starts in a dissolver where sugar is hydrated into a clear solution. That solution then moves to a cooker where heat drives off water and raises solids. The cook endpoint is selected so the base becomes plastic when cooled, not glassy like hard candy, and not fluid like syrup. The endpoint is typically controlled by temperature and by flow resistance in the cooker. If the base is undercooked, it carries too much water and produces a sticky rope that never sets. If overcooked, it becomes too stiff, causing high extruder pressure and surface cracking at the die. After cooking, the hot base is cooled into a window where powders can be incorporated without clumping, and flavors can be added without being stripped. At this stage, the line transitions from a boiling syrup process to a dough making process. Structure formers, like starches, must be dispersed and hydrated evenly. Dry starch added directly to hot syrup would form lumps with dry cores. To avoid that, starch can be fed through high shear mixers or introduced as a slurry that is hydrated and cooked separately before blending. The goal is a continuous matrix where starch and sugars form a cohesive network. Acids and salt are staged as low-rate additions. Acid influences flavor and also changes the behavior of the carbohydrate matrix over time by shifting inversion and hygroscopicity. For that reason, acids are added after the hottest zones and mixed thoroughly but gently. Flavor and color are also added late. Flavor injection is done downstream of intense heat to preserve volatile components. Color is metered as a concentrated solution to avoid adding excess water. Once all components are combined, the mass enters intensive mixing. This is where it becomes a uniform plastic dough. The mixer uses high torque elements that fold and shear. Shear must be sufficient to eliminate streaks and fully wet powders. Shear must not be so aggressive that it whips air into the dough, because trapped air causes bubbles and weak spots in the extruded rope. Mixing endpoint is judged by uniform color, uniform torque, and a stable temperature. Temperature is monitored continuously because the dough must remain plastic but not overly soft. The dough then enters a conditioning stage before extrusion. Conditioning equalizes moisture throughout the mass and stabilizes temperature so extrusion pressure does not pulse. This can be done in a holding hopper with gentle agitation or in a screw conveyor that provides a fixed residence time. The objective is to deliver the extruder a steady feed that produces a steady rope diameter. Extrusion is the primary shaping method. The dough is fed into a screw extruder whose barrel is temperature controlled. The screw compresses and pushes the dough forward. Compression removes minor voids and increases cohesion. Barrel temperature keeps the dough in the plastic range. If the barrel is too cool, pressure rises and the rope surface becomes rough. If too warm, the rope surface becomes tacky and can collapse after exiting the die. The die defines rope, cross-section. Twizzlers ropes are typically round or slightly shaped, depending on the product format. Die temperature is controlled because cold dies cause surface tearing and hot dies cause smear. Pressure at the die is monitored. It acts as an indicator of dough viscosity and hydration. Stable pressure produces stable diameter, which matters because diameter controls final chew and package weight. Immediately after extrusion, the rope is guided by takeoff belts. Belt speed must match extruder output to avoid stretching. Stretching thins the rope and aligns the matrix, which can make the bite tougher and can produce uneven twist definition. The rope is supported so it does not sag, because sag introduces diameter variation and can cause twists to tighten unevenly. Twist formation, when used, is produced by controlled rotation relative to forward motion. A twisting head grips the rope or imparts rotation while the takeoff belt pulls. The twist pitch is set by the ratio of rotational speed to linear speed. A tighter pitch yields a more pronounced twist and slightly denser bite. A looser pitch yields a smoother rope and a softer feel. Twist must be consistent along the rope, because variation creates weak points where the rope can split during cutting or packaging. After twisting, the rope enters the staged drying and cooling tunnels described at the beginning. These tunnels are engineered to hit a final moisture endpoint that supports chew without stickiness. Early tunnel zones focus on removing surface moisture so the rope can be handled without clumping. Later zones allow moisture to migrate from the core to the surface gradually and leave the rope at a stable water activity. Airflow is controlled to avoid whipping ropes into each other, and the rope is kept separated by lane guides. Once the rope reaches the target set, it passes to cutting. Cutting uses rotary blades, or guillotine cutters, synchronized to belt speed. Synchronization controls piece length, and therefore piece weight. Blade sharpness is managed because a dull blade drags and creates strings at the ends. Stringing is a sign that the rope is still too warm or too wet. A clean cut indicates the surface has set and the interior has enough cohesion to fracture neatly at the blade. Cut pieces then go through a short post-set stage. This allows freshly cut ends to dry slightly so pieces do not stick end to end. It also allows any residual heat from cutting friction to dissipate. If a light surface treatment is used to improve flow, it is applied here. A tiny amount of neutral oil can be misted while pieces tumble gently. The oil film reduces surface friction and helps prevent sticking in the wrapper. Oil application is minimal because excess oil changes mouthfeel and attracts dust. Screening can follow to remove fragments created during cutting and conveying. Removing fragments improves pack appearance and reduces dust that can interfere with seals. Metal detection or other final integrity checks can be positioned here because product flow is stable and pieces are separated. Wrapping begins with controlled feeding into flow wrappers. Pieces are aligned into lanes and spaced, so each wrapper cycle receives one piece. Film is formed around the rope and sealed with heat and pressure. Seal dwell and temperature are tuned, so seals are strong without overheating the candy surface, because overheating can soften the rope and deform it under film tension. Film tension is controlled so it sits snug without squeezing the rope flat. Slush. Puppy-style slush is manufactured by producing a shelf-stable flavored concentrate, then engineering a dispensing system that freezes a diluted beverage into a suspension of tiny ice crystals without forming a solid block, then keeping those crystals moving so the product stays scoopable and uniform in a cup. The easiest way to understand the production chain is to start at the point of consumption, the slush machine. A slush machine is essentially a controlled, scraped surface freezer that must keep a mixture right at its freezing curve. It needs enough sugar and solutes to depress the freezing point, enough viscosity to keep ice crystals suspended, and enough agitation to prevent large crystals from growing. Everything that happens in the factory is designed to make a concentrate that, when diluted, behaves correctly inside that machine. The slush machine relies on a mix ratio that is tightly defined. The concentrate is not used full strength. It is diluted with water to a target sugar concentration. If the mix is too weak, freezing point rises and the machine produces a hard ice mass or large crystals that separate into watery and icy zones. If the mix is too strong, freezing point drops too far and the machine struggles to freeze enough, yielding a cold syrup rather than slush. That is why the factory builds the concentrate with a known soluble solids level and a known acidity, and why it specifies a dilution ratio. Concentrate manufacturing begins with water handling and sweetener preparation. Water is filtered to remove suspended solids because solids can seed haze and clog dosing valves. The main sweetener can be sugar syrup, glucose syrup, or a blend. For sugar-based concentrates, granulated sugar is dissolved in heated tanks with agitation until the solution becomes clear. Density is monitored because it defines sweetness and freezing behavior after dilution. For syrup-based sweeteners, the syrup is held warm so viscosity is stable, and metering is accurate. Acidity is set next because pH affects flavor perception and stability. Acid is prepared as a liquid solution for accurate dosing and then injected into the blending tank. pH is measured and adjusted to a narrow set point. A stable pH also helps preserve certain flavor components. Color is handled as a separate dosing stream. It is stored in tanks with gentle mixing and filtered before dosing so it remains uniform. Flavor is prepared as a concentrate that can be dispersed reliably in water. Many slush flavors contain both water-soluble aroma components and oil-based notes. Oil-based components are emulsified so they do not separate in the finished concentrate. Emulsification is done with high shear mixers that reduce droplet size. Droplet size matters because large droplets separate and ring at the surface, while small droplets remain stable and deliver consistent aroma. The finished flavor concentrate is filtered to remove particulate and then metered into the main blending tank. Viscosity modifiers can be included in small amounts to influence mouthfeel and crystal suspension. These components must be fully hydrated and dispersed, so they are added under controlled shear and allowed to mix until uniform. The goal is not a thick beverage, but a mix that can hold microcrystals evenly during dispensing and drinking. Once sweetener, acid, color, flavor, and any stabilizers are in the blending tank, the concentrate is mixed to uniformity without entraining air. Air entrainment can cause foaming in packaging and can affect how the concentrate mixes with water later. The concentrate is then filtered to remove any remaining undissolved particles that could settle or clog dispensing systems at retail. Quality checks on the concentrate focus on soluble solids, pH, color density, and flavor strength. Soluble solids are measured to ensure the dilution ratio will yield the intended freezing point depression. pH is checked for consistency because it affects taste and stability. Color is checked because it must remain stable in storage and consistent from batch to batch. The concentrate then moves to packaging. Packaging is designed for high sugar liquids. Concentrate is filled into jugs, bottles, or bag-in-box systems. Bag-in-box is common because it minimizes oxygen exposure and allows easy dispensing at retail. Filling uses metered valves and is controlled to avoid splashing and foaming. Caps or fitments are applied immediately. Seals are checked because leaks allow contamination and sugar crystallization around closures. Finished packages are coated and cased. At retail, the concentrate is mixed with water to the specified ratio. That mixing can be done in a separate tank or directly in the machine reservoir. The purpose is to produce a ready mix with the correct sugar concentration and acidity. The water used at retail can vary. So many systems specify filtration and cold water use to reduce variability. Inside the slush machine, freezing is achieved by a refrigerated cylinder and a rotating scraper. The cylinder wall is cooled below the freezing point of the mix. A thin layer of ice forms on the cold wall. The scraper continuously removes that ice layer and breaks it into small crystals that are pushed into the bulk liquid. Continuous scraping prevents the ice from building into a solid sheet that would block heat transfer. The rotating mechanism also keeps the entire mixture moving so ice crystals remain suspended rather than settling. The formation of microcrystals is controlled by the freezing point depression of the mix. Sugar and dissolved solids lower the freezing point so the mixture does not freeze solid at typical machine temperatures. Instead, a fraction of the water freezes as ice, while the remaining liquid becomes more concentrated. This concentrated liquid phase acts as a lubricating syrup between ice crystals. The machine aims for a steady balance where ice fraction stays in a target range. Agitation speed is a key control. If agitation is too slow, ice crystals grow larger and the product becomes coarse and icy. If agitation is too fast, the mixture can incorporate air and become foamy, and frictional heat can reduce freezing efficiency. The scraper geometry and clearance are engineered to remove ice efficiently without creating excessive shear that would heat the mixture. The machine also relies on viscosity to prevent separation. If the liquid phase is too thin, ice crystals can settle and form a dense, icy bottom layer, while the top becomes watery. A slightly more viscous liquid phase helps keep crystals evenly distributed. This is why concentrates often include small amounts of stabilizer and why the soluble solids level is strictly maintained. Temperature control in the machine is staged through a thermostat system that cycles refrigeration. The goal is not a constant deep freeze, but a controlled temperature near the mix's freezing curve. If the machine overcools, ice fraction rises too high, and the product becomes stiff and difficult to dispense. If it undercools, ice fraction drops, and the product becomes slushy syrup. Machines often use sensors that monitor torque on the agitator as an indirect measure of slush stiffness, adjusting cooling accordingly. From a factory perspective, this machine behavior drives the formulation targets. The concentrate must produce a ready mix with a predictable freezing curve. That means controlling sugar type and concentration. Different sugars and syrups depress freezing point differently and change viscosity. The factory chooses a sweetener system that creates the desired crystal fraction at typical machine temperatures. Acidity and flavor intensity are also tuned with the machine in mind. Cold temperatures reduce flavor perception. Therefore, the ready mix is formulated with enough flavor concentration to remain noticeable when frozen. Acidity can provide brightness that cuts through cold dullness. However, acidity also affects the stability of certain emulsions and can influence syrup behavior over time. The factory balances these factors. Color stability is another practical requirement. Slush is displayed in clear machine bowls and must remain visually uniform. Colorants must remain stable under light exposure and cold temperatures. The factory filters concentrate to remove particles that would settle and create gradient bands.